What if the planet beneath their feet, the planet that cradled every human story to date, was still mostly a closed book? What if 80% of Earth's own surface, the ground that anchors memory and myth, remained unmapped, unread, and, in many ways, unknown? The idea lands like a contradiction. A species that has steered machines to another world, that has walked robotic feet across the dusty plains of Mars and captured cathedral-like panoramas of distant moons, and yet has only brushed the skin of its own home. The narrator observes this contradiction without judgment, only a slow, gathering astonishment. It is not recklessness that created the gap, but circumstance, light, pressure, time, and the long patience of geological processes. Collectively, humanity stands before vast chambers of unexamined reality, 3 in particular, and feels the smallness of its knowledge as keenly as one might feel the chill when walking into a vast, dark church on a winter morning. Those 3 realms are, in turn, the ocean's deepest reaches, the perennial ice that caps and buries ancient worlds, and the hidden depths below the crust where rock remembers in strained and patchy ways. Each holds its own style of secrecy. Each erases and preserves, hides and reveals. Each invites a different kind of imagination, scientific curiosity that feels like exploration, philosophical unease, and a speculative whisper about things that might have lived or might still live beyond the thin veil of human scrutiny. The deep ocean begins as an absence of light. The narrator describes it as an immense, patient blackness that has swallowed more time than human history can count. Sound becomes the language of those who try to map it, sonar pings that bounce from ridge to abyss, returning only cold, blunt answers. The instruments that skim the surface, ships bristling with equipment, drifting arrays, autonomous submersibles, are tiny beacons against a dark ruled by pressure. Where light dies soon after leaving the sun's reach, pressure builds in layers like a thought pressing downward. The vehicles that descend into these depths are engineered to survive in a place that was not designed for human presence. Hulls thick as trust, cameras that steal back a sliver of visibility, lights that mimic the bioluminescent tongues of living things. Descriptions of scenes enlarge, the slow lowering of a submersible through blue into navy into a black, so absolute that the only reference point is the glow of its own lamps. The sudden, disorienting reveal of a landscape of chimneys and vents, where black smoke blooms from the earth and life congregates around chemical heat rather than sunlight. The narrator leans into imagery. Forests of tube worms waving in a current that smells of iron and sulfur. Ghostly crustaceans tracing the edges of a vent like pale thoughts skittering around a campfire. These are the deep ocean's pockets of known wonder, places that explorers have been allowed to glimpse. Yet they are islands of illumination in a sea-sized unknown. Beneath the surface, the map remains sketchy. Much of the ocean floor is a blank of low-resolution data, sonar sweeps that paint topography in broad strokes, satellite altimetry that hints at mountains and trenches, but not at the fissures between them. The narrator notes an unsettling fact. Parts of other planets are charted with more fidelity than the deep basins of the world that feeds them. This comparison is meant not to shame, but to prod. It highlights a human pattern. Curiosity directed outward often outruns curiosity inward. It also reveals a practical truth. To look deep into the sea requires more than instruments. It demands time, money, and the tolerance of environments that chew up metal and patience alike. The emotional texture here is complex. There is awe, a teetering, delighted sense of being shown something unimaginable. There is anxiety, a worry about what else might be living down there, what evolutionary experiments are unfolding in places humanity has never seen. There is tenderness, too, when the narrator lingers on the idea that some animals are bioluminescent, tiny living lanterns making a life in a world of perpetual night. Above all, there is a certain humility. The oceans do not care to be known. They continue their slow rearrangements, entombing what winds and waves sweep to their mouths. If the ocean's secrecy is black and fluid, ice's secrecy is white and numbingly patient. The story of ice is a story of archives. The narrator brings forward the notion that ice is a time capsule, a slow-pressed ledger where seasons are inscribed like rings inside a tree. Drilling into an ice sheet is like coaxing speech out of a not-yet-awakened archive. Each cylindrical core is a compressed narrative of atmosphere, of ash, of pollen, of greenhouse gases frozen into bubble-sized phrases. Here, beneath kilometers of compacted white, lie records of climates and weather that stretch back hundreds of thousands of years. Those records have answered questions about past temperatures and atmospheric compositions, but they have also asked new questions about stability, about fragility, about events no living memory can recall. Detailed vignettes grow into longer scenes, a drill bit slowly turning, metal grinding against ancient ice, the steady spool of core being drawn upward, its innards revealed in pale bands like pages torn from a book, technicians examining each layer under stark lamps, translating bubbles into years and years into stories of volcanic winter and warm stretches. But alongside the careful work is another image that complicates the archive. The ice moves. It flows like a river that keeps its cool biting into entire landscapes, carrying sediments and secrets deep into the empire of the frozen plain. Underneath ice sheets may lie rivers and lakes that have not seen the sky in millions of years. Subglacial Lake Vostok, a dark inland sea sealed for eons, slips into the narrative as a place that could harbour life forms adapted to isolation or preserve organic fragments of an ancient surface now altered beyond recognition. There is also a melancholic tone. Ice preserves but also conceals. As the climate warms, ice melts and releases its trapped stories, but not always in neat sequences. Melt can scramble archives, obliterate fragile surface features, and scatter remains across changing landscapes. The narrator lets the listener linger on the analogy. Ice is like a library in a slow-motion flood, shelves tilting, books dislodged, pages flying. The emotional register here is a combination of respect for the ice's custodianship and dread at the speed with which these guardians can fail. The third realm, the rock itself, the deep subsurface, the geological engine, is a different kind of secrecy. Where ocean darkness and sheeted ice conceal by weight and cold, the lithosphere conceals by time and transformation. The narrator frames this part with a striking image. The crust is not a static museum, but a palimpsest, a manuscript overwritten and erased over and over by tectonic ink. Mountains grow and fold, then become plains. Sediments bury the remains of the past and are themselves consumed by the great conveyor belt of plate tectonics. Rocks remember, but their memories are partial and translated through heat and pressure. Scenes stretch into grander scale. The slow closing of an ocean basin, the grinding of continental plates, the blackness of subduction zones where entire sea floors vanish into a boiling, suffocating depth. The narrator explains how, over millions of years, the solid earth recycles itself. The very processes that allowed life to flourish also erased the footprints of what might have come before. Fossils that were once plentiful are squashed, metamorphosed, or mixed into impossible puzzles. The record that survives is fragmentary, biased toward environments that favor preservation. Hard parts, rapid burial, and depositional calm. Cities, buildings, the artifacts of technology, if they ever existed very far back in time, would meet a terrible and patient fate under the slow hand of geology. Stone becomes silk in plate-scale times, metal rusts and disperses, structures are buried, crushed, remade. Here, speculation is tempered with geological rigor. The narrator does not spin wild tales, but rather shows the mechanisms of erasure. Subduction zones swallow continental shelves whole, dragging any evidence into conditions that melt and reset their chemistry. Surface erosion grinds memory down to molecular anonymity. Even the most durable of human creations are ephemeral on timescales measured in millions of years. The voice is not nihilistic but solicitous. It urges a sober appreciation of time's power and of how little permanence even the most solid achievements hold in the face of Earth's slow, remorseless processes. Across these three domains, a theme emerges. The planet keeps most of its secrets, not by malevolence, but by the sheer nature of its systems. Darkness, cold, pressure, time, and chemical transformation are not conspirators, they are processes. Yet together they form a regime of concealment that renders Earth, for all its familiarity, an unfamiliar place. The narrator points out a striking paradox that fuels both wonder and unease. Human beings, for all their ingenuity, are young animals on a planet governed by very long clocks. They have begun to read fragments of the story, but the margins remain unread, the middle chapters missing, and the deeper appendices locked in inaccessible vaults. Emotion threads through the account. There is the curiosity that drives expeditions. The compulsion to lower a camera into black water, to bore into a glacier, to set off seismic waves and listen for their echoes beneath the crust. There is also a kind of existential humility, the recognition that human history is but a single breath in a long planetary poem. The narrator shapes this sentiment with care, neither sentimentalizing nor dismissing. It is both a caution and an invitation. If humanity truly wishes to know the planet, it must accept that knowledge will be slow and eccentric, a mosaic built from sparse tiles rather than a single, coherent mural. Speculation finds room at the margins of these meditations. The narrator allows certain possibilities to shimmer without asserting them as fact. Could life persist in ways unfamiliar to them in the cold, pressurized dark? Could subglacial lakes shelter microbial communities evolved along an alternate set of environmental rules? Could complex, non-technological ecosystems have dominated ephemeral landscapes lost to mantle churn? These are not fantastical fantasies, but reasonable ponderings. They invite the listener to imagine the breadth of biological possibility when the constraints are so different from the human norm. Finally, the narrator circles back to the opening idea with a renewed sense of gravity. The 80% unseen is not simply a statistic. It is an emotional and intellectual condition. It means that their maps are partial, their histories incomplete, and their assumptions about permanence suspect. It means that new discoveries can still upend old certainties, that the planet may yet reveal ecosystems and processes no one had imagined, and that the record of the past, what it preserves and what it loses, is an active player in the story humans tell about themselves. The concluding image is deliberately open, a world in which most of the stage remains in shadow, where every beam of light drawn across the darkness reveals as much absence as presence. The narrator poses a question that will carry forward like a current under an iceberg. If so much of Earth remains unseen, what should they seek, and why should they care? It is a question of curiosity and responsibility, of the hunger to know and the humility to recognize time's scale. The answer, the narrator hints, will unfold in the parts to come. But it begins here, in the awareness that the planet has kept its greatest secrets, not in spite of them, but because of the slow, indifferent systems that make Earth both tender and implacable. What does it mean to live on a planet whose most intimate surfaces remain, in a practical sense, unreadable? The question arrives quietly, like the first soft ping from a ship's transducer, an ordinary mechanical sound that nevertheless implies an enormous absence. More than 80% of the ocean, a vast, moving skin that encases the continents, has yet to be mapped at resolutions that would turn the unknown into something intelligible. That statistic is not merely an assertion about cartography, it is an admission about perception. It means most of the world's relief, most of its scars and sculptures, its tombs and laboratories still exists only as suggestion. The deep ocean is not merely distant, it is a regime. It is an environment that redefines ordinary words. Light becomes rumour, temperature becomes a narrow badge of survival, and pressure becomes a moral force of the physical world. Pressure increases by roughly 1 atmosphere for every 10 meters of descent. At the abyssal plain 3 to 6 kilometers down, the weight of water presses like an idea repeated until it becomes belief, hundreds of times the pressure at the surface. At the hadal depths, in the trenches that topple the ocean into almost mythic seams, pressures approach or exceed 11,000 meters of atmosphere equivalent force. Steel and silicon can be made to hold against such compression, but the effort is exacting and expensive. Above all, pressure is not an occasional inconvenience. It is a long, quiet fact that structures everything that happens there. The methods used to know these depths are themselves framed by limitation. Multi-beam sonar arrays ride along on research vessels, painting stripes across the ocean in pings and echoes. Satellite altimetry infers seafloor shape from minute undulations in the sea surface caused by gravity anomalies. Autonomous underwater vehicles and remotely operated vehicles descend and crawl like conscious tools. Yet each method trades scale for detail, speed for intimacy. Satellite maps offer global breadth, but blur the seafloor into tens or hundreds of meters per pixel. Shipboard sonars produce higher fidelity, but are constrained by time at sea and by the simple size of the oceans. AUVs can achieve exquisite resolution over small areas, discovering chimneys and rubble and fields of organisms behaving on their own timescales. But one autonomous vehicle can explore only a tiny fraction of a trench or abyss. The result is a mosaic in which lowly tiles of high-definition knowledge are separated by oceans of low-resolution ignorance. Imagine the descent. A winch releases a cable. A small cylindrical vessel is lowered inch by meticulous inch. The sea above appears at first as light blue glass. A few minutes later, the sun's color is a memory. Lamps designed to mimic biological bioluminescence flare to life. On the surface, the ship's crew is a chorus of precise motions, but the real choreography is mechanical. Pressure sensors ticking, camera shutters opening, transducers mapping. The vessel's hull, often constructed from titanium spheres or syntactic foam, creaks with a sound that belongs less to metal and more to time. The craft slips into depths where the only clock is the slow movement of particles and the ponderous, patient metabolism of the planet itself. Lights on a submersible do not recreate daybreak. They report presence. They reveal, in sudden theatricality, spires of mineral deposits that glow like ruined cathedrals. Hydrothermal vents, where superheated water meets cold abyssal currents, belch mineral-rich plumes that sustain ecosystems uncoupled from sunlight. Around these vents proliferate organisms that would be fanciful if described in any other context. Tube worms taller than a person's arm, their red plumes tasting chemical gradients instead of air. Blind shrimp whose antennae read the chemistry of the water like fingers reading braille. Bacteria that derive energy from hydrogen sulfide, arranging themselves into luminous carpets. These vent communities are islands of clarity, precise and local miracles. yet they sit like theatre flares in a black ocean that otherwise refuses to illuminate its secrets. There is a particular hush to these scenes. The cameras, the lights, the mechanical arms, all are instruments of translation, trying to turn a world shaped by pressures and timescales alien to human intuition into images and numbers. The narrator of this world story, the collective voice of those who map and measure, is forced to become a translator of absences. For every vent field discovered and celebrated, there are thousands of square kilometers of abyssal plain that remain, for all practical purposes, anonymous. Vast stretches of the deep ocean are covered by slow-moving muds that bury and erase with a patience unmatched by wind or river. Currents shift sediments across geological time in processes that would render immediate artifacts invisible to a human timescale. The ocean's capacity to bury and erase extends beyond the slow creep of mud. Turbidity currents, fast, sediment-laden avalanches that course down submarine canyons, can scour a slope clean and sweep any structure into obfuscation. These events are not rare. Over geologic time, they rediscover and redistribute the surface, smothering bones, shards, and possible remnants of past activity into new contexts. Rivers that once flowed across plains and carried sediments are now under hundreds of meters of seawater. Their channels are preserved in the seafloor in low-resolution hints, visible from high-altitude altimetry as elongated shadows. But in many cases, their finer features remain unreadable without expensive, time-consuming surveys. The emotional valence of these realities is complicated. There is wonder, an almost childlike amazement, that life can and does exist without sunlight, that chemistry alone can sustain complex webs of organisms. There is also unease, an acknowledgement of how little the human species has interfaced with these depths, and of how misleading certainty can feel when based on a few bright spots of knowledge amid a dark sea. The deep ocean imposes a humility on thought. It insists that humans are not the measure of all ecological possibility, nor are their means of observing sufficient to pronounce comprehensive truths about the planet. Speculation finds its place at the edges of these data-poor regions, but speculation here must bow to the sea's known mechanics. If there were to be biological communities that persist in the deep outside the familiar zones, complex, long-lived ecosystems that have evolved over millions of years in isolation, they would likely be adapted to gradients of pressure and chemistry, not to the rhythms of surface life. These adaptations might result in creatures with slow metabolisms, reproductive cycles spread thin across decades, and biochemistries glittering with divergence. The idea is not science fiction, it is an extension of observed reality. Extremophiles already exhibit molecular chemistries that challenge historical expectations about where life can subsist. The deep ocean suggests that life's palette is broader than the surface brushstrokes that have shaped the human imagination. The question of preservation returns with urgency when the topic shifts from life to artifacts. If a long-forgotten technological civilization had risen on the planet during a period when sea levels were markedly different, an Arctic melt, a late glacial high stand, what would remain today? The geological answer is blunt and unsentimental. Shorelines migrate. Coastal settlements are buried under meters or tens of meters of sediment or drowned beneath thousands of meters of seawater. Chemical processes in seawater corrode metal artifacts. Alkaline and acidic interactions dissolve organic matter over time. The plate tectonic engine recycles crustal fragments. The processes that build, bury, and erase are not targeted. They are indifferent. They convert surfaces into strata, surfaces of occupation into layers of sediment and stone. The deeper the time interval, the more complete the erasure. On timescales of millions of years, most direct traces of past structures vanish into the general chemistry of the crust. Yet the ocean is not a perfect eraser. Under certain circumstances, hints persist. Rapid burial in anoxic conditions can slow decay dramatically. Cold, deep waters with low oxygen can preserve organic materials for millennia. Submerged landscapes sometimes become time capsules if they are promptly covered by sediments that exclude oxygen and scavengers. Still, the likelihood of finding a clear, unambiguous signal, a structure recognizable as technological after millions of years of geological processing, is small. The more probable outcome is a diffuse, ambiguous trace, anomalies in sediment composition, unexpected concentrations of certain isotopes, scatterings of artifacts without context. To interpret such traces requires frameworks that accept ambiguity, that weigh probabilistic signals against the planet's natural tendency toward rearrangement. Human efforts to pierce the darkness are as much about method as imagination. New sonar techniques and swarms of autonomous vehicles promise to shrink the mapped unknown, but at great cost. A full, high-resolution map of the ocean floor would demand a scale of sustained surveying unlike anything in human history. Ships at sea for years, instruments deployed and retrieved, immense quantities of data to be processed and stored. The technical challenge is also cultural and economic. Funding follows perceived priorities. Curiosity must compete with immediate human needs. The result is a patchwork of attention. Spectacular discoveries make headlines. The slow, grinding work of cataloguing the abyss proceeds in relative obscurity. There is a philosophical turning in that reality. The fact that more of Mars is mapped in detail than the Earth's deepest basins is instructive not because it indicts explorers, but because it reveals human patterns of attention. Symbols and frontiers attract. The narratives humankind tells about itself, that exploration is conquest. That mapping equals mastery. Push outward into the dramatic. The moon, the planets, the stars. At the same time, the nearest great unknown remains beneath their feet, patient and thorough in its indifference. This paradox is not merely rhetorical. It shapes the kinds of questions asked, the instruments designed, and the priorities set. The deep ocean is an indictment of human short attention spans as much as it is a challenge to scientific methodology. And yet, there is a moral and an aesthetic urgency to the endeavor. The deep ocean is not merely a vault of potential curiosities, it is a living system that regulates climate, cycles nutrients, and hosts biodiversity essential to planetary function. Understanding it matters for reasons beyond the romance of discovery. Deep currents sequester carbon, abyssal sediments store long-term records of atmospheric composition. Seafloor communities recycle materials that affect surface productivity. Ignorance is not a neutral state when it masks processes that feed back into the climates and biospheres upon which human futures depend. The deep ocean's darkness is therefore both a scientific problem and an existential one. It is a problem because the methods of knowledge are expensive and slow, and because the signal-to-noise ratio of discovery is often discouraging. It is existential because the planet's capacity to hide and erase means that human narratives of origin and continuity are constructed on slender evidence. To accept that most of Earth's own topography is a mystery is to accept a form of intellectual humility. To build knowledge as if each new datum might contradict an old certainty, and to treat the planet's silence as substantive information rather than a mere hiatus. The deep sea, in this sense, functions as a mirror. It reflects back the species that seeks to know it, their ingenuity, their limitations, their impatience, and their capacity for reverence. When a light pierces the abyss and reveals a field of tube worms clustered around a vent like a congregation around a living furnace, the moment elicits an immediate aesthetic reaction. There is, in that instant, an impression of being small and fortunate, of witnessing a detail of the planet's choreography that few will ever see. Such moments are the narratives that energize further exploration. They are the justification in the court of wonder. But the greater drama lies in the cumulative truth that the world keeps most of its depths to itself. The ocean's unmet majority is not a lacuna to be filled quickly, it is a long-term project of attention, humility, and resource allocation. The imperative is not simply to know, but to learn how to learn from a planet that writes in slow, cautious fonts, in pressure, in sediment, and in chemical gradients. The deep ocean asks for patience, for instruments capable of persistent presence, for analytic frameworks that accept partial, ambiguous signals as the basis for discovery. In the end, the fact that 80% of the ocean remains unmapped is not a failure so much as an invitation. It is an invitation to think across scales, to understand that time is an active force and that the planet's capacity to obscure is as meaningful as its willingness to reveal. It invites an ethic of exploration that prizes careful, long-duration observation over flashy conquest. It asks the listener to imagine a planet whose most intimate archives are not locked by intent, but by processes, by weight, by chemistry, by time, and to respond with curiosity that is patient enough to match them. So the narrative returns to its opening question with a quiet insistence. In a world where most of the skin remains unread, what does it mean to claim understanding? The answer, at least for now, is to admit the smallness of human maps, to honor the depth's indifference, and to continue the slow work of turning pings into pictures, silences into data, and absences into the possibility of discovery. The ocean will not be hurried. It will be known at its own dreadful, generous pace. What if the planet's seams were not just invisible seams, but open thresholds, places where the outer skin of water became a doorway into the slow workshop beneath the crust? The notion is simple but unsettling. The sea floor is not merely a buried landscape, it is a working hinge between the living skin of the planet and the vast machinery of rock and heat beneath. Down there, darkness is absolute. Temperatures switch from sub-zero to scalding in the span of a meter, and pressures become a continual, devouring presence. Those extremes shape life and chemistry in ways that seem almost like a different grammar of existence. They also shape how Earth remembers its past and how it hides it. The deep ocean is, in the most literal sense, a darkness that eats light. Sunlight fails within the first few hundred meters. The remainder of the water column is a night without dawn. Within that night, human instruments are the only fleeting stars. Cameras and floodlights carve theatrical cones out of the black, revealing forms that could have been imagined as monsters in stories. Towering chimneys belching mineral smoke, clusters of white plumes hanging like gutted organs above a fissure. Pale, jointed animals that move with a slowness that is not laziness, but calculation measured by chemistry rather than seasons. The catalogue of oddities already recorded in those depths reads like an index of inventions. Tube worms taller than a person's arm wrapped around mineral spires, crustaceans equipped with antennae that taste sulfide, crabs that farm bacterial lawns on their claws, and blind fish whose senses are tuned to electricity and faint vibration rather than light. These discoveries are not perverse curiosities, they are clues. They suggest that biology finds ways to occupy niches when sunlight is absent and pressure is relentless. Temperature is a contradiction in this black world. Most deep ocean water sits a fraction above freezing, a slow refrigerator cold medium through which life moves conversely sluggish and steady. Yet along mid-ocean ridges, and at hydrothermal vents, chemistry turns theatrical. Superheated fluids, once in contact with magma beneath the crust, surge upward to meet the cold abyss. When they do, minerals precipitate, forming chimneys that puff out dark, metal-rich smoke. The black smokers. Within millimeters, the temperature drops from hundreds of degrees Celsius to nearly ambient, creating one of the sharpest gradients on the planet. Those gradients, so violent by everyday standards, are stable according to geological time. They become the engines for entire ecosystems that ignore sunlight. Microorganisms oxidize hydrogen sulfide and methane, converting chemical energy into biomass and, in doing so, support communities of organisms that have evolved along an independent axis from the sunlit world above. The seafloor thus behaves as a mediator. It is a place where heat and rock touch sea and life. That mediation is not merely superficial. The porous oceanic crust is a sponge of currents, a conduit for circulation that carries water and dissolved chemicals into the lithosphere and then back out again. Fluids percolate through basaltic layer after layer, reacting with rock in processes like serpentinization, a chemical transformation that releases hydrogen. That hydrogen becomes a ready food source for microbes. In these dark, mineral-rich interstices, life persists not because sunlight arrives, but because the planet's own heat and chemistry provide a steady, if meager, supply of free energy. The result is a subsurface biosphere, a sometimes slow, often ancient community of organisms that lives within sediments and within the oceanic crust itself. Estimates made by many researchers point toward a vast, hidden microbial world beneath the seafloor that, in the rough logic of magnitude, may represent a significant fraction of Earth's total biomass. It is a biosphere of long timescales, low metabolism, and an independence from the rhythms of day and season that govern the surface. Seen this way, the seafloor is more than a habitat, it is a gate. Fractures, faults, and permeable basalts are doors that open inward. In places where tectonic plates spread, hot rock rises and generates new crust, and seawater percolates, takes heat and chemistry on its back, and returns changed. In areas of subduction, surface sediments and oceanic crust are drawn down into the mantle. In between, hydrothermal systems act as both furnaces and filters, extracting material from the deep and releasing it with new signatures. The seafloor is where the interior and the exterior converse. It is through that conversation that the planet exchanges carbon and metals, that it shapes the chemistry available to the biosphere, and that it buries and sometimes preserves the traces of surface events. Those same processes make the seafloor a powerful agent of erasure. The blackness of the abyssal plain is often carpeted with a slow rain of fine particles. Ejecta from distant currents, microscopic skeletal remains, volcanic ash. Over tens of thousands or millions of years, such a rain buries and anonymizes. Where rivers once carved landscapes on the continental shelf, those features are now brushed by sediment and drowned beneath hundreds of meters of water. Turbidity currents, fast-moving underwater avalanches, can scour a canyon clean, shift a shoreline's sediment load, and scatter any deposited materials into oblivion. It is a double act. The seafloor is both a protector and a destroyer. Under anoxic, rapidly buried conditions, organic material can be preserved for geological timescales. Under more exposed, oxygenated conditions, it is dissolved and dispersed until only chemical signatures remain. It is within that tension between preservation and destruction that speculative questions take hold. If large, unusual biological forms evolved in the seafloor's cold dark, they might persist on timescales that dwarf human history. If genetic lineages split and ran largely independent of surface ecologies, Their duration and diversity could be vast beyond imagination. There is a sober science behind such propositions. Genetic studies of deep biosphere organisms show lineages that are distinct, slow to evolve, and adapted to chemical energy sources in ways that suggest long periods of isolation. These patterns invite a philosophical turn. The planet's most stable habitats may not be mountain ranges or tropical forests, but rather the slow-moving mat of microbes and chemoautotrophs that line cracks and subsurface pores. Habitats whose timescales are governed by diffusion and reaction rather than seasons and storms. This is why the seafloor is a gateway in the epistemic sense as well. To probe it is to reach toward a part of Earth's biography written in chemistry and pressure rather than in light and stories. A sediment core is not a simple sample. It is a rolled ledger of particle flux, climate signal, volcanic events, and biological presence. One that must be read with patience and humility. Likewise, a drill into the basaltic crust is not only an engineering feat, but also an essay into habitability at pressure and temperature combinations that do not dominate human experience. Each core, each borehole, and each return sample is like a fragment of a palimpsest, partial, slurred, and layered by the planet's own editing. Yet, the practicalities of looking through those doors are exacting. Pressure, for one, is not a background condition, it is a constant sculptor. At the deepest trenches, pressure surpasses 1,000 atmospheres, an environment in which molecules behave slightly differently, where gas solubilities change and where materials designed for surface tasks fail in quiet ways. Thermal gradients strain instruments. Corrosive chemistry eats electronics and metal. Optical systems are starved of photons. All of this makes exploration an act of concession. Humans must design proxies, accept slow rates of return, and rely on machines capable of persistent, patient operation. It is a form of endurance. The cost is not only monetary but also cognitive, simply because the data arrive in fits and fits of fits. A spectacular vent field 1 week, 10 quiet kilometers of abyssal plain the next. The mosaic of knowledge is wildly uneven. There is, too, a moral dimension to this ignorance. The seafloor's role in sequestering carbon, in cycling nutrients, and in moderating ocean chemistry means that what remains unknown is not harmless. Understanding the depths is part of understanding the planet's long-term resilience. For example, deep-sea sediments store records of atmospheric composition through trapped microfossils and isotopic signatures. Hydrothermal activity influences mineral distribution and ocean chemistry in ways that can feed back into climate over geological timescales. To ignore the seafloor's agency is to mistake the surface for the whole machine. The gate beneath the water opens onto processes that matter to the future as much as they matter to the past. Speculation about unknown life in the deep must be anchored to these constraints. Evolution under pressure and resource limitation tends towards strategies that prioritize efficiency and longevity. Slow metabolisms, long life cycles, and scarce but efficient reproduction. Complex multicellular life, if it exists extensively in the subsurface, would likely be structured by a calculus very different from that of a shallow reef. That life might be rare in biomass, but ancient in continuity. It might weave relationships not by daylight competition, but through chemical symbioses, through cooperative webs knitted out of energy gradients rather than seasonal abundance. It is an image of life as a creaking subterranean clockwork, slow, precise, and indifferent to human notions of urgency. And then there is another voice in the room, the archaeological, speculative one that wonders about traces of former surface technologies. The geological response again is blunt. The seafloor favors obliteration. Coastal settlements will be drowned with sea level changes, metallic objects corrode, organic materials decay unless buried swiftly in low oxygen sediments. But there are corner cases. Cold, oxygen-poor basins preserve wood and plant remains for tens of thousands of years. Rapid burial in anoxic layers can encapsulate materials and slow chemical decay. Chemical anomalies, unusual isotope ratios, concentrations of rare elements in layers that do not match natural cycles, could act as signatures of anomalous processes. Such anomalies would be subtle, statistical, and ambiguous. Interpreting them would require a new kind of forensic patience, a willingness to see patterns in noise and to weigh the probability of extraordinary explanations against the planet's usual indifference. Through all of this runs a human feeling, an ache of both smallness and compulsion. The deep ocean turns the species' habitual scale inside out. Centuries of civilization are a single grain of sediment in an abyssal stratigraphy that stretches for millions of years. Yet that grain can contain molecules and isotopes that speak of rapid events, of sudden meltings, of fires and agriculture. The challenge is not merely technical, it is psychological. To engage with the seafloor is to learn how to think in vastly longer registers of time and in registers of process that do not align with intuition. It is to accept that knowledge will be patchy, that certainty will be probabilistic, and that some answers may arrive decades or even centuries after they are first sought. The seafloor as gateway carries one last quiet lesson. Gates are two-sided. They permit access into the interior, but they also mediate what the interior permits to the surface. Hydrothermal vents release metals and heat. Subduction locks carbon into the mantle. Sediments that are compacted and buried remove organic matter from the active cycle for vast spans of time. That reciprocity matters. The processes operating at the ocean floor are not passive backdrops. They are prime movers in Earth's long story. To stand at the edge of that gate metaphorically, through instruments and observation, is to witness the planet's method of self-keeping, of trading, transforming, burying, and occasionally revealing. The narrative that will unfold in later parts is rooted in this hinge. To know Earth is to learn the grammar of its thresholds, to read the seams where water meets rock, and to listen for the faint chemical languages that flow between them. If the seafloor keeps secrets, it keeps them in a manner that is neither malign nor conspiratorial. It keeps them in the impartial language of pressure and time, of mineral precipitation and sediment drift. That manner forces humility. It asks patience. It offers, in return, some of the most profound answers possible about origins, continuity, and the range of life. The deep ocean is a door into Earth's inner workshop. To open it is to enter the slow economy of planetary change. The species that seeks to understand must therefore adjust its tempo. The curiosity that once built rockets must learn to build long-duration presences, machines and alliances that can live in darkness, measure in centuries, and listen to the chemical whispers the seafloor always has been sending. Only then will those thresholds stop being mute and begin, at last, to speak. What if the planet's seams were not merely scars to be charted, but literal apertures, fissures that yawn and lead downward into regimes of pressure and heat where the rules that govern surface life are rearranged? What if some of the most consequential archives on Earth were not safe in museums or libraries, but hidden in the places where water becomes a conveyor and ice becomes a vault, in Hadal chasms that lead toward the mantle, and in ice sheets that lock air like language trapped in amber? The image is abrupt, a throat in the planet, dark and immense. The Mariana Trench, the deepest of these wounds, is not a single, tidy hole. It is a complex of scarred slopes, choked canyons, and silted basins that slope into the abyss. To imagine descending there is to imagine standing at the lip of a cathedral whose vault opens into a pressure so great that a human body would be flattened in an instant. The Haddle world is a geography written in extremes, temperatures that hover near freezing, pressures that rise with breathless implacability, and a lighting so absent that the only stars belong to instruments. When explorers lower a cage of metal and cameras into that quiet, the machinery becomes a translator between scales. A winch hums, a small, egg-shaped submersible slips past the twilight zone and into a dark that is not merely lack of light, but an entire alternative of sensation. Hulls designed with spherical logic creak almost poetically under stress. Instruments register microfractures in real time. The first images that return are theatrical. Fields of soft sediment, like deserts of ash, a ghostly snailfish pressing itself against a slope, amphipods waving their translucent legs like slow, solemn processions. Later, in other zones of the trench, black smokers and fissures appear, not in the Marianas' deepest hollows perhaps, but across mid-ocean ridges and back-arc basins, where the ocean floor becomes a seam and the crater mouth a speaker for the planet's internal voice. Those hydrothermal vents do something both intimate and strange. They pour out water scalded by magma, carrying with it an inventory of elements scraped from the lithosphere. Where hot, mineral-laden fluids meet cold, abyssal seawater, minerals precipitate and build towering chimneys. The chemistry of these chimneys is unusual and revealing. Polymetallic sulfides rich in copper, iron, zinc, and sometimes traces of precious metals, manganese nodules studding the plains like fossilized clams. Carbonate structures in alkaline systems such as the Lost City, where serpentinization, the chemical embrace of water and peridotite, releases hydrogen and fuels ecosystems by chemical, not solar, energy. Those strange minerals are more than curiosities. They are palimpsests that record interactions between rock, water, and heat. They trap isotopic signatures and microscopic life. They form chemical microhabitats that host organisms dependent on sulfide oxidation or methane consumption. In the filtrate of a black smoker, bacteria that would make Darwin tilt his head flourish, building the base of food webs that do not rely on sunlight. Tube worms and clams cluster around vents like congregations, their physiology rewriting what it means to be dependent on the sun. Here, chemistry becomes the currency of life, and it is a currency issued by the planet's interior. But vents and ridges are not purely generators of life. They are also windows and mouths. Fractures that open along spreading centers and transform faults permit seawater to infiltrate the crust. In such places, fluids circulate, react, and return, sometimes altered in ways that change ocean chemistry on large scales. Elsewhere, trenches act as conveyors of oblivion, subduction zones where entire oceanic plates, along with their sediments and anything they carry, are dragged down into the mantle. That gravitational swallowing is a brutal but essential part of Earth's recycling economy. The same process that builds arcs of volcanoes and spawns new crust also erases surfaces and hides histories. A shoreline once lined with settlements is not simply drowned. Over millions of years, it can be consumed and chemically reconstituted. There is a paradox here. The very processes that produce rich, sustaining niches, vents, fractures, hydrothermal circulation also participate in erasure. Turbidity currents, submarine avalanches of mud and rock, can scour canyons and bury anything left on a slope. Sedimentation rains down over centuries and millennia until channels that were once rivers become sealed beneath meters or kilometers of sediment. In that slow burial, Biological and cultural traces are anonymized. Bones and pottery, if present at all, become indistinguishable components of strata. Yet under exceptional conditions, rapid anoxic burial, cold abyssal temperatures, quick isolation, remarkable preservation can occur. Organic material may persist far longer than intuition permits. The sea floor is therefore both a destroyer and a conservator, writing and redacting the planet's narratives in the same breath. The Hadal world and its events pose questions not only about biology, but about signs. What counts as evidence of a past presence? When the ocean buries and reworks, what remains are often patterns in chemistry, concentrations of particular isotopes, layers of ash that speak of a distant eruption, anomalies in metal distribution. The clues are statistical and ambiguous rather than pictorially obvious. To read them requires a patience and a humility that acceptance of geological pacing offers, an understanding that the planet's memory is partial and probabilistic, written in gradients and traces rather than in complete chapters. Then there is the ice, an opposite sort of archive that conserves by arresting motion rather than by burial. Greenland and Antarctica are planetary black boxes. They do not, as popular metaphors sometimes suggest, imprison singular stories. Instead, they accumulate, layer by layer, year upon year, atmospheric breath upon atmospheric breath. Each snowfall compresses the last, and as the weight mounts, bubbles of ancient air are sealed in the crystal lattice. Those bubbles are time capsules, compact vignettes of past atmospheres, carrying proportions of greenhouse gases, traces of ash, pollen, volcanic aerosols, and now, in more recent layers, the fingerprints of industriality, lead isotopes, black carbon, and the first signatures of synthetic molecules. The act of drilling into an ice sheet is a kind of extraction of silence. A drill descends, a core is coaxed upward in a thin cylinder that is an arrested stratigraphy. The core reveals bands like pages of a ledger, whiter, dustier, darker, each band correlating with seasons, storms, or extraordinary events. Inside, gas bubbles are counted and analyzed. Isotopes of oxygen and hydrogen are measured to infer temperature. Trapped particulates are mapped to volcanic eruptions. Trapped methane spikes mark abrupt episodes whose causes are still debated. The deepest cores, like the Epica stack, or the cores from Dome C and Vostok, are among humanity's most intimate peeks into the planet's pre-industrial atmospheres, reaching back hundreds of thousands of years. They tell of glacial maxima and interglacial warmth, of the slow juxtapositions between cold and warm that have set planetary climates for epochs. There is a strange tenderness to these cores. They are silent archives that do not shout. Their testimony arrives through patient laboratory translation. Technicians slice millimeters and measure molecules, converting layer thicknesses, bubble concentrations, and isotopic ratios into narratives about methane fluxes or abrupt climate oscillations. The story they coax is austere. Ice does not embellish. It preserves with an economy that serves both discovery and dread. For the more recent bands, dusts carry microplastics and industrial markers, a small, clinical note confirming that the Anthropocene has left a chemical harbinger cosmically legible even to instruments 1,000 years hence. Yet ice is not immutable. The sheet moves, it flows, fractures and carves. Crevasses and moulins open like ventilation shafts, funneling surface meltwater toward the bed. There, under kilometers of ice, lakes and rivers move in secret. Subglacial Lake Vostok, isolated for millions of years beneath Antarctic ice, reads like science fiction in its implications. A lake sealed from the sky, possibly biochemically unique, a place where life could have evolved under radically different constraints. The methods used to access such places, hot water drilling, sterile sampling, are exercises in caution and humility. There are ethical and scientific debates over contamination and over whether the value of access outweighs the risk of altering an ancient, closed system. The ice conceals, but it also isolates, preserving ecosystems in a chemical time capsule that may predate current surface ecologies. There is urgency woven through that preservation. As the planet warms, the great sheets surrender their layers. Melt unlocks trapped gases, releases ancient carbon and methane from permafrost and gas hydrates, and reveals microbial communities or genetic fragments locked away for millennia. The release is not neat. It can be chaotic. Ice that has served as a chronological ledger can, under rapid thaw, shred its record, scattering material and scrambling stratigraphy. The library analogy returns with cruelty. Shelves tipped, labels dissolved, the sequence of volumes lost. The very artifacts that have allowed reconstruction of planetary history are vulnerable to the same forces whose signatures they preserve. That vulnerability generates an ethical tone that moves beyond curiosity. Greenland and Antarctica are not only archives, they are proxies for planetary stability. The gases trapped within them are not passive inscriptions, but actors in climate systems. When their seals open, they alter radiative balances, feed feedback loops, and complicate predictions. The black box metaphor is therefore dual. These ice masses are repositories of past atmospheres and also potential amplifiers of future change. Their integrity matters not only to paleoclimatology, but to the lived futures of human societies. Across trenches, vents, and ice, the planet houses different registers of memory. Trenches lead down and sometimes away, shifting surface signals into the mantle's slow, heat-driven rewrites. Hydrothermal vents articulate exchanges between rock and water, manufacturing niches of life and mineral signatures that persist in the chemical record. Ice encapsulates atmospheric moments with crystalline fidelity until the moment of release. Together, they form a distributed archival system. Some records are particulate and local, others gaseous and global. Some are locked in mineral matrices, others in bubbles of air. Each archive has its own grammar of preservation and erasure. The emotional tenor when confronting these systems is complex. There is awe at the cunning of life that lives without sunlight, at the engineering that allows humans to peer briefly into trenches and vents. There is melancholy at the recognition that so many stories will remain partial and ambiguous, that the planet's own processes are indifferent to the human desire for complete narratives. There is also a sharpened urgency, not merely scientific but moral. In the face of thawing ice and industrial footprints that are increasingly legible downcore, the black boxes are not merely curiosities, they are records whose contents, once released, may change the script. Speculation is permitted, but it must be tethered to process. The vents speak of ecosystems that could persist on chemical energy for vast spans. The trenches remind that the planet recycles and erases. The ice shows that even the air itself can be cordoned and later liberated. To imagine a deep past of unknown biospheres or lost technologies is to engage seriously with the physical economies that would have to preserve or erase such things. Good speculation listens to the planet's pace and yields hypotheses that can be tested by isotopes, by sedimentology, by trapped gases. The story, then, is not one of secret conspiracies, but of patient systems. It is a narrative that asks the listener to recalibrate time and scale, to acknowledge that some of Earth's most meaningful archives are not on display, but are buried, submerged, or frozen, and that knowing them requires machinery, patience, and a humility that matches geological modesty. The planet keeps its deepest records in seams and boxes, in fissures that descend toward the mantle, and in ice that seals the sky. The work ahead is to read these registries with care, to translate pressure, chemistry, and trapped air into narratives that extend the species' comprehension of where they came from and where they might yet be carried. What if the archives of the planet were not only written in rock and sediment, but were also folded into slow, white seals, chambers of water and time locked beneath kilometers of ice, unread for millions of years? And what if those seals were beginning to unfurl? The question itself is quietly unsettling. The same warming that redraws coastlines and fattens seas also peels back the planet's most guarded folios. When ice melts, it does not simply let water run, it releases an entire chemistry of memory. It loosens trapped gases, liberates organic matter, and, in places, reconnects living surfaces to ecosystems that have been isolated since the age of mammoths or earlier. The thaw is not merely a physical transformation, it is an unspooling of history, biological, chemical, and, possibly, microbial. Beneath Antarctic and Greenland ice sheets lie places that, in any ordinary human imagination, amount to bunkers of the ancient world. Subglacial lakes, fed by slow refreezing and insulated from atmospheric exchange by great columns of ice, have existed in isolation for timescales that can stretch into millions of years. These are not shallow ponds. They are dark seas the size of cities and, in at least one case, a lake with a surface larger than Lake Ontario. Their surfaces know only the hush of ice above them. Their waters have not tasted rain, wind, or sunlight in epochs. To imagine lowering a probe into one of these benthic oceans is to imagine listening in on a conversation that began long before human reckoning. The seduction of those waters is scientific and philosophical at once. If life persisted there, it would have done so under constraints utterly different from those that shaped life at the surface. Sunlight, the great driver for most ecosystems, is absent. Instead, energy must be extracted from rock, from chemical gradients, from the slow diffusion of molecules pressed out by pressure and pressure-driven chemistry. The vocabulary of metabolism in such places is less about photosynthesis and more about chemolithotrophy. Microorganisms that oxidize reduced minerals, microbes that metabolize hydrogen generated by serpentinization in the bedrock, archaea that exploit methane seeping from sub-ice sediments. The result could be a biosphere whose rhythms are measured not in seasons but in millennia. Life strategies that favor dormancy, extreme efficiency, and biochemical rearrangements unseen in sun-warmed ecologies. The possibility of finding ancient bacteria, strains that have been isolated and evolving along rare branches of the tree of life, carries the aura of a discovery that would rewrite some margins of understanding. But the allure is tempered by the tangle of probability and preservation. DNA breaks down, molecules degrade. The longer the isolation, the more likely complex biomolecules had been hydrolyzed, cross-linked, or otherwise altered. What might persist is not intact genomes, but fragmentary signatures, lipids with unusual side chains, stable isotope ratios betraying metabolic pathways, rare biominerals precipitated by microbial mats, or enzyme relics that hint at biochemical strategies. In short, the evidence will be subtle, forensic, and often ambiguous. It will demand patient, multidisciplinary reading, paleogenomics, lipidomics, isotopic ecology, and a willingness to treat noise as possible signal. Accessing those waters has already become a moral and technical crucible. Drilling into a sealed lake is not merely an engineering feat, it is a decision that folds together curiosity, hubris, and planetary ethics. The history of attempts is instructive. In the early 21st century, Russian teams reached toward Lake Vostok with a mix of triumph and controversy. Later projects, such as the drilling into Lake Whillans, showcased a different model: careful, small-scale, and sterile to an unprecedented degree. The methods themselves betray the fact that contact is as likely to contaminate as it is to reveal. Hot water drills, designed to melt a hole and let a probe slip through, must be filtered and sterilized beyond the usual practices of fieldwork. Any microbe introduced from the surface risks altering the very ecosystem it seeks to study, and any loosening of ancient microbes carries, in theory, risks, biological, ecological, and epistemic. That last clause warrants emphasis. The risk is as much about knowledge as about biohazard. Contamination confounds inference. A surface microbe that hitchhikes down a drill line could be mistaken for an ancient endemic organism. A modern bacterium that outcompetes a slow-adapted, low-metabolism native could alter the lake before anyone has a chance to observe it. The science literature around subglacial exploration is thus as much a literature of protocol as it is of hypotheses. Sterility is the ethic, uncertainty is the reality. Many argue with moral clarity that the precautionary principle should govern access. If the act of studying a place destroys the thing studied or makes its origins indecipherable, then the value of knowing cannot justify the loss. Those ethical debates are not simply abstract. They intersect with a pressing new axis of consequence: climate-driven exposure. Ice that has been stable for millennia is now shifting, thinning, and sometimes collapsing. Meltwater percolation, surface radiation, and warmer ocean incursions under ice shelves all conspire to fracture the seals. Where once the only pathway for exchange was through a painstakingly sterilized borehole, now natural meltwater channels and subglacial outflows can connect a sealed lake to the surface in years or decades. The result is a kind of uncontrolled experiment at planetary scale. Where previously scientists could control entry points and procedures, climate change opens doors unpredictably and indiscriminately. That opening has multiple consequences. First, there is the straightforward biogeochemical effect. Ancient organic carbon locked in ice and permafrost thaws and becomes available for microbial decomposition. Microbial communities that had been quiescent or constrained by cold are reawakened, and their respiration can produce greenhouse gases, CO2 and methane, that feed back into warming. Permafrost soils contain vast amounts of carbon, and their thawing represents one of the largest potential amplifiers of anthropogenic climate change. Secondly, pulses of fresh water from melting continental ice dilute local ocean salinity, which can disrupt oceanic circulation patterns. Freshwater influx onto continental shelves and into the North Atlantic has the potential, at large scales, to slow or alter the thermohaline circulation, with cascading climatic implications. Beyond these well-documented systemic effects, there is a subtler ecological consequence: the release of microbial assemblages into ecosystems for which they are not adapted, or, conversely, the sudden exposure of contemporary communities to ancient microbes. In a coastal context, meltwater can carry nutrients and microbes into coastal seas, fueling blooms and shifting trophic dynamics. Where ancient microbes find hospitable niches, they might join, alter, or be outcompeted by existing communities. Predicting which outcome will dominate is exceedingly difficult. Ecological invasions and integrations are governed by contingent histories and microscale interactions that resist simple modeling. Speculative scenarios of revived pathogens, tropes that populate popular imagination, require careful unpicking. The persistence of viruses and bacteria over tens of thousands of years is constrained by nucleic acid stability, host availability, and environmental conditions. Many viruses require living hosts. Without continuity of host lineages, their viability wanes rapidly. There are documented cases of microbes revived from permafrost after thousands of years, and there are ancient viruses detected in ice cores. But revival does not equal pathogenic threat. Most organisms in these pockets will be specialized to extreme conditions far removed from human physiology. That said, prudence is not hubris. The responsible posture is to couple curiosity with containment, to treat recovered organisms with rigorous safety protocols, to ask the right questions in the right sequence, and to avoid sensational claims when the data are fragmentary. The thaw also rewrites the planet's chemical ledger. Trapped gases in bubbles, once liberated, enter the atmosphere with immediacy. Organic matter once locked in permafrost becomes substrate for respiration. Hydrates on continental margins may destabilize as temperatures and pressures change. These are not mere footnotes in Earth history. They are amplifiers. They convert ancient storage into active flux. The paleoclimate record, the story of abrupt events like the Younger Dryas, warns that the planet's climate has tipping points that can flip faster than human institutions can adapt. The contemporary thaw places them into new alignment with human-driven forcings, producing a compound risk rarely seen in the paleo record. A confluence of warming, melt-driven hydrology and released carbon that can accelerate change on timeframes relevant to civilization. There is, amid these physical processes, a narrative of responsibility. Humanity's curiosity has historically been its most luminous trait, driving it to probe dark seas and sealed lakes. Yet curiosity untethered from precaution has a history of unintended consequences. The locked subglacial ecosystems are, in effect, legacies of planetary processes. The decision facing the species is not simply what to discover, but how to steward discovery in ways that preserve the integrity of those places and the safety of broader biospheres. International protocols, environmental ethics, and a cosmopolitan view of stewardship become essential. These are our archives not only of biology, but of planetary history, and they belong to a temporal constituency that extends beyond the present generation. The emerging field of environmental forensics will be central to reading these releases. When ice relinquishes a layer of pollen, ash, or microplastic, the interpretation requires context, a stratigraphic framework, isotopic calibration, and an acknowledgement of the disturbance that thaw can cause. Rapid melt can scramble layers, mix deposits, and produce palimpsests that are difficult to parse. To find an unambiguous signal, a biomarker, or an isotopic anomaly that clearly points to an ancient, isolated process will therefore be rare. More common will be messy, partial datasets that demand statistical patience and humility. Yet, the thaw also offers possibility. The release of previously locked nutrients could bolster productivity in certain coastal systems, drawing carbon into biological stocks in the short run. Ancient DNA fragments could illuminate evolutionary histories erased from the surface record. Isotopic pulses could add resolution to paleoclimatic reconstructions. Every released signal, if read carefully, provides another tile in the mosaic of Earth's deep time narrative. The difficulty lies not in the absence of value, but in the complexity of extracting it without destroying the medium that carries it. Emotion threads quietly through these scientific and ethical concerns. For many, there is a sense of mourning, for ice as a preserver, for the slow, quiet patience of frozen systems now truncated by human warmth. There is also a muted exhilaration, the scientist's version of awe. at the prospect of peeking into an ecosystem shaped by processes outside the modern human sensory palette. But beneath both lies anxiety, an awareness that the very act of revelation is entangled with loss. The thaw is simultaneous disclosure and dispossession. It returns stories to the surface even as it destroys the conditions that allowed those stories to be preserved. The moral of this unfolding chapter, then, is not a prescription, but an attitude. The species that seeks to know these white vaults must approach with a blend of reverence and restraint. When the ice yields its secrets, the next steps will matter as much as the discoveries themselves. Protocols for sterile sampling, international agreements on access, and a commitment to transparency in the interpretation of ambiguous data will all be tests of maturity. To peer into an ancient lake is not merely to collect data, it is to accept custodianship over a piece of Earth's deep biography. In the end, the thaw raises a question as old as exploration. When confronted with the unknown, what is one willing to risk for knowledge? This time, the stakes are planetary. Melting ice will continue to unseal chapters of Earth's past, whether humanity is ready or not. The challenge is to match curiosity with care, to read the rising secrets with a humility that honors both the fragility of the ecosystems revealed and the fragile vantage point of the readers. The white seals are breaking. What emerges will demand attention, interpretation, and a kind of ethical patience commensurate with the long histories these waters have kept. What if the most audacious instrument of human curiosity was a tube? A slender, unprepossessing cylinder that, driven by horsepower and torque, promised to translate the planet's immense, slow grammar into something readable. The idea is simple and stubborn. To know what the deep earth keeps secret, they must pierce its skin. Drilling is a kind of insistence, a refusal to let time and pressure alone tell the story. It is also an act that turns attention inward, away from the tides of exploration that once carried rockets into space and toward a very different kind of frontier, one measured in meters of rock, degrees of heat, and the patient calculus of geology. The era of deep drilling began with modest ambitions and enormous symbols. Project Mohole, an ephemeral mid-century dream, sought to puncture the Earth's crust and reach the moho, the boundary between crust and mantle. It failed on the scale of dreams, not for lack of hope, but because the Atlantic and political currents were stronger than drilling rigs and grant applications. The Kola super deep borehole, begun by Soviet engineers, lasted longer and went deeper, over 12,000 meters downward into the Kola Peninsula, an achievement that read like a confession about both technical prowess and planetary stubbornness. The German KTB project probed into crystalline crust in Bavaria, and the more recent age of oceanic drilling has produced ships like Chikyu, designed to lower heavy drill strings into abyssal waters and sample the living crust beneath spreading ridges. Each project is a ritual. A platform rises, a derrick groans to life, and pipe by pipe the bore string descends. There is a particular choreography to coring. The rotation, the careful retrieval, the slow unwinding of thousands of meters of pipe, the instruments that translate pressure into telemetry and rock into language. When a core returns, it is quietly ceremonious. Within its frozen cylinder are fragments of time, broken grains of mineral, palimpsests of chemical exchange, veins of fluid, pockets of gas. Labs receive these cores like archives received by archivists. Technicians in white coats treat the samples like the fragile remnants of a library burned and partially reconstructed. They slice, photograph, and measure, coaxing isotopes and molecules into testimony. What drilling projects have shown, repeatedly and with a humility that borders on astonishment, is that the planet resists simple narratives. At Kola, temperatures rose faster with depth than expected. At a depth where engineers had presumed to find conditions amenable to simple drilling, Heat turned rock plastic and tools began to fail. The crust was not the neat stack of layers penned in textbooks, but a dynamic, porous, and chemically reactive medium. The oceanic drilling initiatives revealed that basalt is not an impermeable husk, but a sponge through which seawater circulates, reacts, and emerges changed. The deep biosphere, microbes in sediments and within the pores of basalt, emerged not as an exotic footnote, but as a profound and inconvenient reality. Life persisted far below sunlight's pale reach, tethered instead to mineral gradients and chemical energy flows. To stand at the lip of a deep borehole is to confront two intertwined feelings. One is exhilaration, the sense that a new scale of the planet's biography is about to be read. The other is a restrained fear, not cinematic alarm, but the sober awareness that disturbing an ancient closed system carries unknown consequences. The deep is not empty. It is a patient, functioning ecology in places, a chemistry in slow motion in others. When a drill punctures a sealed pocket, the release may be physically dramatic. A plume of fluids, a sudden change in pressure, a gush of methane. Or it may be almost invisible, a trail of dissolved ions bleeding into a new medium. Either way, the act of access converts a temporal repository into a present process. The possibility of resurrecting ancient biological material from depth is at once a scientific temptation and an ethical puzzle. The deep biosphere contains organisms whose metabolisms are measured in years or decades rather than days. Microbes that divide slowly, that subsist upon hydrogen released by rock serpentinization, that oxidize iron and sulfur in chemical economies alien to sunlight-based food webs. Some of these lineages have diverged early in Earth's history and may carry biochemical strategies novel to modern biology. The prospect of finding enzymes with unusual catalytic properties, lipids with strange stability, or genetic relics that illuminate the earliest chapters of life is intoxicating to researchers. Such discoveries would expand a narrative of biology and possibly offer clues about life on other worlds. But contaminating a closed system with modern organisms is not merely a methodological error, it is a moral hazard. A surface microbe introduced by a drill string could outcompete a slow-growing endemic community, erasing what remained of a fragile evolutionary experiment before it can be read. Sterilization becomes not a procedural nicety, but a duty. The memory of earlier, cruder penetrations hangs over the field like a cautionary tale. Where access is uncontrolled, inference is compromised. For that reason, every ambitious bore, every plan to sample a subglacial lake or a sealed aquifer arrives braided with protocols. Filters, sterilization, clean room sampling, and debates about whether some places should remain unread. Beyond the question of contamination lies the spectre that animates popular imagination and unsettles careful minds alike. Ancient pathogens. The possibility that bacteria or viruses dormant for millennia could be revived by the warmth of the surface or by new hosts is not an assertion of impending doom, it is a risk calculus. Many microbes, particularly viruses requiring host continuity, decay over geological time as nucleic acids fragment. Virulent spectres evolve in the crucible of host pathogen co-evolution. An organism adapted to deep, high-pressure chemistries is unlikely to thrive in lungs and bloodstream. Yet the burden of proof rests on prudence, not on optimism. The existence of viable microbes revived from permafrost or ice in the past demonstrates that under certain conditions, survival is possible. The consequence of unanticipated survival demands circumspection. What is required, therefore, is not dramatization, but methodical containment and public governance that treats rare, low probability risks with the seriousness of their consequences. Drilling can also awaken geochemical processes with outsized effects. Deep fluids are repositories of dissolved gases and reduced compounds. A borehole that connects an ancient, pressurized reservoir to the surface could liberate methane quickly, perturbing local chemistry and, at scale, releasing greenhouse gases locked away for eons. Hydrothermal systems, once breached or altered, can change the chemical signature of seawater, influencing trace metal availability and, in some regions, nutrient cycles. The Earth's crust is not merely a storehouse, it is a set of coupled systems. Changes in one pocket can cascade, slowly or suddenly, into others. There are physical hazards, too, that are less speculative than they feel. Wells that destabilize surrounding rock, induce subsidence or alter stress fields in faults, pressurized fluids that create blowouts, the triggering, insensitive tectonic settings of seismicity. Engineering mitigations exist, but they are not foolproof. Every bore is an intervention into a system whose equilibrium can be far from obvious. The governance challenge emerges from this intersection of curiosity, risk, and consequence. Who decides which boreholes may be made? What international frameworks regulate attempts to pierce subglacial lakes or the continental mantle? Presently, scientific norms and national interests form an uneasy mosaic. There are respected international protocols for sterilization and for environmental impact assessment, but they are unevenly applied and depend often on the good faith of researchers and funders. The very nature of deep drilling, expensive, technical, and sometimes cloaked in strategic significance, means that private and state actors may approach it with differing priorities. That variance in intention raises questions not merely of safety, but of stewardship. Should some chapters of the Earth's book remain closed to preserve the integrity of ecosystems and records? The precautionary principle, borrowed from environmental ethics, suggests that in the absence of certainty about impacts, restraint is warranted. At the same time, there is an argument that knowledge gained from deep drilling can be a public good of immense value. Paleoclimatic records extracted from bore cores illuminate ancient climates and help calibrate models that forecast future change. Samples from the deep biosphere expand understanding of biochemical possibilities and may underpin bioengineering advances or novel biotechnologies. Drilling into an impact structure reveals the mechanics of mass extinction events. Penetrating basaltic crust reveals pathways of heat and chemicals that shape ocean chemistry. Each successful bore pushes the boundary of human knowledge, informing decisions about climate resilience, resource stewardship, and planetary stewardship. A true measure of these endeavors is the humility with which they are undertaken. The most instructive episodes in drilling history are those in which discovery led to more questions than answers. The surprise of higher than expected temperatures at Kola, the revelation that microbial life persists where it had not been anticipated, the evidence that the crust is more permeable and more chemically alive than textbooks suggested. Each surprise demanded a recalibration of assumptions. The narrative that emerges is not one of conquest, but of ongoing apprenticeship. Humans learning, snafu by snafu, to listen to the planet's own constraints. There is a particular moral colour to that apprenticeship. Deep drilling is an exercise in temporal responsibility. The course taken today will tell stories to descendants who may not be yet born. The contamination a careless bore introduces will persist on geological timescales beyond any single political mandate. The ethic, therefore, is intergenerational. Decisions about whether and how to drill should account for the rights of future readers of the planet's archives. That framing turns technical questions into matters of civic virtue. Speculation, finally, must be disciplined by process. The scenarios that populate fiction, ancient, monstrous pathogens, subterranean civilizations, or sentient chemistries, are useful as thought experiments because they sharpen protocols and governance. They expose where uncertainties are largest and where safeguards are weakest. Real prudence is quieter. It lives in the design of sterilization rigs, in the peer review of environmental impact plans, in multinational agreements that constrain unilateral penetration of planetary reservoirs. It is manifest in long-term monitoring after a bore is completed, in data sharing that allows for independent interpretation, and in a refusal to prioritize novelty over safety. In the end, the decision to bore deep is an expression of humanity's characteristic contradiction. There is an insatiable curiosity, a longing to read the planet's margins, that sits beside an appreciation for the planet's slow, indifferent processes. To pierce the skin of Earth is to place instruments into the hands of those who must both ask and answer difficult ethical questions. The drill bit does not know why it descends, it obeys torque and weight. The humans who plan and watch must supply justification, caution, and a depth of moral thought commensurate with the depths they explore. The door into Earth's interior is not a single aperture, but a protocol: when to open, how cleanly, and with what humility. The histories of Kola, mohole attempts, KTB, Chikyu, and modern ocean and continental drilling are cumulatively a record of both bravery and lesson learning. They suggest that the greatest discoveries will not come from brute penetration alone, but from the slow alliance of engineering, ethics, and patience. If the deep holds relics of ancient fauna, if it shelters microbes whose biochemistry enlarges life's definition, or if it hides traces of past worlds reworked beyond recognition by tectonic patience, those revelations should arrive to a species prepared to accept both the beauty of the finding and the weight of the responsibility that comes with having opened the book. What if the planet's very heart were not merely a physical center, but a kind of memory palace so distant and so fiercely private that every attempt to read its inscriptions has been thwarted by sheer scale? The image will not be a surface scene, not a mountain or an ice field, but a distance, 12 kilometers downward, and then an absence that stretches more than 6,000. 12 kilometers is where human hands and machines have, in recorded history, reached with confidence. 6,000 plus kilometers is where the core waits, an abyss of pressure and temperature that remains, in practical terms, a locked room. That disparity is the dramatic framing for this chapter. The human reach scratched the skin, the planet's heart remains unread. The technical limit is blunt and stubborn. The deepest human-made hole, the product of decades of engineering, knowledge, and stamina, penetrated barely beyond the brittle upper crust and the young, human-shaped archives it holds. A handful of drilling projects, ambitious, fevered, triumphant in their smaller aims, pushed downward into kilometers of rock, and what they delivered was often more puzzlement than clarity. Instruments and materials designed for a world of air and modest temperatures learned to fail in ways that were instructive. Bits that fused, pipes that bowed under unexpected heat, sensors overwhelmed by pressures that made mundane calibrations meaningless. The outer Earth is not inert. It resists probing by altering conditions at depth in subtle, often unanticipated ways. In that resistance lies the first lesson. To reach the core is not a matter of engineering alone, but of matching endurance with humility. What lies beyond the reach of iron and steel is known only through its echoes. The primary instrument for seeing toward the center is seismic sound, the planet's own voice. Earthquakes generate waves that curve, reflect, and refract through layered media. Those waves arrive at distant observatories as altered rhythms. From differences in travel time and in the polarization of seismic waves, in the ways some waves vanish and others appear, scientists have painted a layered portrait. It is elegant and maddeningly imprecise. A thin, rigid lithosphere, a plastically flowing mantle, a core with two principal characters, an outer shell that is liquid and an inner heart that is solid. The outer core churns like a slow, viscous ocean of iron and nickel. The inner core stands as a small, crystalline kernel, denser and different in texture. Yet the core's theoretical architecture, tidy on a diagram, hides more questions than it answers. Temperatures estimated at the boundary between the inner core and the outer reach values rivaling the surface of the Sun, thousands of degrees, while pressures are unquantifiably immense. Under such conditions, familiar chemistry yields to behaviors little encountered in laboratories. Minerals adopt phases that were once the province of hypothesis, and metals travel between states in ways that challenge intuition. Laboratory proxies, diamond anvil cells, shock compression experiments, and high-powered synchrotrons help, but they are simulations at a remove. They tell a story about behavior under extreme conditions, not the living narrative of a slowly evolving planetary core. It is in the irregularities of the data that the core's personality becomes manifest. Seismic anisotropy, the observation that waves travel faster in some directions than others through the inner core, hints at an internal architecture that is oriented, perhaps crystalline, perhaps layered. Some measurements imply that the inner core rotates slightly faster than the surface, a phenomenon called superrotation. Others suggest that different hemispheres of the inner core behave differently, as if one side learned a different geologic history from the other. These subtleties look like traces of ancient events, asymmetric growth, uneven crystallization, latent flows in the outer core guiding the inner core's accretion. Then there are the thermal anomalies. The calculated heat flux at the core mantle boundary is heterogeneous. Patches where heat leaks more briskly into the base of the mantle, other regions where insulating chemical piles seem to trap warmth, fostering long-lived thermal structures known as LLSVPs, large, low shear velocity provinces. Those LLSVPs are strange, enormous blobs at the base of the mantle that move slowly, hold anomalous chemistry, and influence where plumes rise to create hotspots at the surface. They are, in a sense, the planet's deep bruises, patterns in a skin slowly repainted by internal convective rhythms. The core is not merely a source of heat, it is the dynamo that has given Earth its magnetic personality. The convecting outer core, electrically conductive and violently mobile on geological timescales, generates the geomagnetic field by a process of self-sustaining induction. The magnetic field is not static. It wiggles and drifts. At times it weakens, at times it flips. A global reorientation recorded in the slow cooling of volcanic rocks and in the long ledger of paleomagnetic strata. Modern measurements reveal perplexing anomalies. The field has regional weaknesses and distortions, the most notable being a broad, persistent depression over the South Atlantic, a thinning of the magnetic buffer that allows more energetic particles to reach low Earth orbit. The magnetic poles wander. The field experiences sudden jerks in secular variation. These are not mere curiosities. They are signposts of processes deep below, hints that the dynamo's flows are neither uniform nor simple. Those magnetic oddities carry practical consequences for the species that lives on the crust. Satellites and power grids feel the field's tremors. Cosmic and solar particles exploit its pauses. But the symbolic consequence is perhaps greater. The geomagnetic record is one of the primary, durable traces of the planet's deep history, a long, slowly written palimpsest embedded in ocean-floor basalts and spewed volcanic lavas. Paleomagnetism provides timing, direction, and the irregular punctuation of reversals, a text written by the core mantle conversation and preserved at the surface just long enough to be read by patient scientists. It is one of the few direct links between processes in the inaccessible deep and the geological record left above. If the core is a dynamo, it is also a recycler. Subducted slabs sink toward the mantle, carrying with them heavy metals, hydrogen, carbon, and other components that eventually may be drawn toward the core mantle boundary, remixed and sometimes returned in mantle plumes that feed oceans of basalts on the surface. The circulation of matter on planetary scales is relentless and unkind to fragile records. Surface signatures can be dragged down, heated, and chemically rewritten. Rocks that once carried fossils and structures may find their atoms redistributed, their isotopic story dissolved into averages. The core plays a role in the grand erasure. It is the endpoint of a geologic economy that consumes the past to make room for the future. Within that economy, anomalies in temperature and magnetism acquire a narrative weight. They are not eccentricities to be chalked up to measurement error. They are parts of a broader architecture where chemical stratification and thermal heterogeneity at the base of the mantle influence the patterns of surface volcanism, where a blob of dense material jostles the slow churn of the mantle and thereby nudges a chain of volcanoes into life. The planet preserves echoes of ancient events as heterogeneities, a late veneer of metal added by meteoritic impacts, pockets enriched by incompatible elements during early differentiation, residues of ancient crystallization. Those chemical memories survive not as neat artifacts, but as variations in seismic speed and as local heat fluxes. Through painstaking mapping and imaginative synthesis, geophysicists have begun to read those whispers as stories of early Earth. Giant impacts, the crystallization of an early magma ocean, and the slow chemical sorting that followed. Technology has pushed the boundary of inference as far as it can. Seismic networks, global and dense, have raised the clarity of the echoes. Neutrino detectors and muon tomography are spoken of with increasing seriousness as tools that might one day probe in ways seismology cannot. Mineral physics experiments, using ever more extreme conditions, have revealed iron's possible phases, potential alloys with light elements, and the way impurities alter conduction and rheology at core conditions. Yet nothing replaces direct contact. No probe, no cable, no instrument can descend intact into the outer core or return samples from the inner. The energies at play render such ambitions for now purely speculative. The gulf between 12 kilometers and 6,000 is not merely a matter of distance, but of orders of magnitude in pressure, heat, and material behavior. This reality shapes the tone of any speculation about the core's capacity to preserve traces of ancient bulwarks. If some improbable non-surface-based archive had been buried, could it endure the journey into the deep? The geological answer is uncompromising. The core and lower mantle are not repositories that cradle human-scale artifacts. They are furnaces and grinders. Any macroscopic structure would be annihilated. Even the most robust synthetic materials would be chemically altered, mechanically deformed, and ultimately dissolved into their constituent atoms. What survives in the long run is distribution, isotopic signatures, unusual concentrations of elements, lattice defects, and perhaps subtle variations in noble gas ratios. These are the sorts of signals a sophisticated laboratory with good stratigraphic context might pass and link to processes that occurred billions of years ago. They are not, however, pictures or artifacts waiting like time capsules to be unearthed. There is a different set of possibilities that lie closer to plausibility. The core and the base of the mantle might contain chemical fossils of the early planet, pockets of material that escaped thorough mixing during the planet's formative chaos. The blobs seen in seismic tomography could be repositories of primordial chemistry preserved by their density and isolation. If so, they are invaluable archives for understanding differentiation, how iron separated from silicate, how volatiles were partitioned, and how the planet's initial inventory of heat-producing elements was distributed. Those archives, if archives they are, preserve no inscription in the human sense. Instead, they are geological dictionaries whose words are isotopic ratios and mineral assemblages. Interpreting them requires patient laboratory translation, careful modeling, and an acceptance of ambiguity. The emotional register of all this is layered. There is a profound, almost vertiginous humility invoked by the numbers that the species that can put a probe into interplanetary space has only whispered into its own planet's ear. There is also an exhilaration. The core's secrets are the most consequential for planetary habitability. The dynamo deflects charged particles and preserves atmosphere. The heat engine shapes mantle circulation and thus the locations of continents, oceans, and volcanic outgassing that feed climate. To understand the core is to understand a central axis of Earth's long-term habitability. The stakes are scientific and existential. There is, finally, a philosophical cadence to the inaccessibility. Much of Earth's biography, the early differentiation, the great impacts, the slow growth of the inner core, is recorded not in tidy documents, but in the planet's physical gradients. Those gradients are legible only through patient decoding. The technological limit at 12 kilometers and the core's remoteness are not merely a lament about unbuilt machinery, they are a reminder about the kinds of questions that demand different instruments, not ones that drill harder, but ones that listen longer, simulate more faithfully, and synthesize across disciplines. The heart of the planet keeps its own tempo. It will reveal itself sparsely, in tremors and in magnetic whispers, in the chemistry of lavas and the stubborn anomalies at the base of the mantle. For a species that measures its history in centuries and its attention in headlines, that tempo is both frustrating and humbling. Yet within that frustration is fertile ground for a different virtue, the patient curiosity that accepts the long conversation. If the inner machinery has imprinted the planet with signatures of its earliest epochs, then unraveling them will be an act of collective patience, not conquest. To read the heart is to become, in a sense, a better listener, attuned to the slow, anisotropic murmurs of a world whose most intimate pages lie bound in pressure, heat, and magnetic flux. The question that remains is not merely technical. What will the species do with the time required to learn? The core keeps its secrets, but it does not do so out of malice. It guards a narrative written on scales that dwarf human lives. To pursue it is to accept the discipline of deep time, and to accept that some answers will arrive only to those willing to wait, to measure, and to listen. What if the planet's invisible skin, the soft, shifting web of magnetism that habitually goes unnoticed, suddenly began to speak with a voice that was not only louder, but stranger? The idea is deceptively simple. Earth has a magnetic field because somewhere deep below, molten iron is moving and, in that motion, it generates a living, changing shield. That shield has protected life, shepherded atmosphere, and tuned the planet's interaction with space for hundreds of millions of years. Yet in recent decades, instruments sensitive enough to hear the hum have begun reporting changes that are less a steady background and more the staccato of a system in motion. Poles slipping, local weaknesses blooming, pulses and jerks that arrive like unexpected clauses in a long geological sentence. The magnetic field is, in the most practical sense, a guardian. Charged particles from the sun are deflected and channeled along field lines. Cosmic radiation that would otherwise batter the atmosphere is partly held at bay. Without it, the thin membrane of air that makes complex life possible would slowly thin under the onslaught of solar wind and energetic particles. It is no small thing to have a planetary-scale magnet, yet for all its importance, the field is not a fixed monument. It is a dynamic, emergent property of motion and heat deep within the planet, a phenomenon of electricity and fluid dynamics, of turbulence and induction. Like weather in the atmosphere, the geomagnetic field evolves, flares, and sometimes behaves in ways that surprise the steady hands of prediction. Two kinds of observation have driven recent unease and curiosity. The first is ordinary motion writ at planetary scale. The magnetic poles wander. The North Magnetic Pole has been migrating in fits and accelerations across the Arctic towards Siberia. The South, too, is on the move. Pole drift is not new. It has been recorded in paleomagnetic rocks that reveal wanderings across millions of years. But the speed of contemporary displacements and the way they are accompanied by a thinning of the field in certain regions is noteworthy. The second observational class is more local but more alarming. The South Atlantic anomaly, a broad region where the field is weaker than surrounding areas and where energetic particles from space can creep closer to the surface, endangering satellites, electronics, and, potentially, high-altitude flight. Together these phenomena read like punctuation marks in a text that ancient rocks have been writing slowly for eons. Changes in the dynamo's behavior are not hypothetical. They are happening now, and they leave discernible traces. How are such things known? The modern age has furnished a suite of listening devices. Satellites like the Swarm constellation, earlier missions such as Champ and Ørsted, networks of ground-based magnetometers, paleomagnetic measurements of cooled lava and sediments. All provide both high-resolution snapshots and longer-term mosaics. Satellites map the field like weather satellites map winds, global, continuous, and sensitive to subtle gradients. Ground observatories capture the local pacing of secular variation and geomagnetic jerks, sudden changes in the rate of the field's evolution that arrive within a human timescale and whose physical origin is still debated. These instruments reveal that the magnetic field is a composition of components. A large-scale dipole that resembles a bar magnet, smaller regional flux patches that wax and wane, and higher frequency phenomena, pulsations and waves in the magnetosphere that respond to solar input. It is the flux patches and their migrations that make the South Atlantic anomaly so interesting. The anomaly is not an accidental hole. It is a manifestation of the dipole being imperfect, of patches of reversed or attenuated flux at the core, mantle boundary projecting upward to the surface. Here, beneath Brazil and the South Atlantic Ocean, field lines bulge and fold in ways that permit a deeper penetration of energetic particles and raise satellite radiation exposure. The anomaly is growing and drifting, and that dynamical behavior has led to speculation, measured, sometimes breathless, about whether a full reversal might be in the offing. Reversals are a normal feature of Earth's long history. The magnetic poles have flipped many times, recorded in the imprints left by cooling lava and in sediments. But the paleo record tells a complicated story. Reversals are neither uniform nor predictable, and their associated environmental effects are ambiguous. Some reversals leave only a faint atmospheric trace. Others coincide with transient increases in cosmogenic isotopes and, perhaps, heightened radiation at the surface. The presence of the SAA does not, by itself, prove an imminent flip. It is one piece in a planetary puzzle. Beyond the big picture motion, there are smaller, stranger signals. Geomagnetic jerks, sudden changes in the secular variation, arrive like punctuation, abrupt accelerations in the field's evolution that propagate across observatory networks within months. These jerks are not seismic in the usual sense. They are not caused by brittle failure in the crust. Instead, they are likely signatures of changes in flow within the outer core. Waves of momentum, torsional oscillations, sudden reorganizations of iron-rich currents that alter the pattern of magnetic induction. In the magnetosphere, electrons and ions dance to a different rhythm. Chorus emissions and Whistler mode waves, coherent radio frequency phenomena generated by energetic particles, create audible, song-like signatures when converted to sound. These are not mysterious in a mystical sense, they are well understood plasma physics. Yet their existence underscores an uncomfortable fact. Earth's magnetic system is not a monolith, but an orchestra with many players, some local, some deep, some driven from outside by the sun, and some arising from the slow, internal convulsions of the deep core itself. Those internal convulsions are where speculation becomes most tempting and also most consequential. The geomagnetic field is generated by the dynamo, convective motions in the electrically conducting fluid outer core that organize, stretch, and amplify magnetic fields. But the dynamo is not a black box with a single dial. It is a complex, emergent system. Buoyancy forces, compositional gradients, light elements being expelled as the inner core grows, heat flux variations at the core, mantle boundary, and mechanical coupling to the mantle all matter. Observations of anisotropy in the inner core's seismic structure, inferences of superrotation relative to the mantle, and the existence of large, slow structures at the base of the mantle, the LLSVPs, suggest a deep coupling between chemistry, flow, and magnetism. In short, the core is dynamic, and its dynamics can leave signatures at the surface, in drifting poles, in weakening patches, in jerks and pulses. If the deep interior writes that much, can it also be read as something more than a physical engine? Here, the narrative slides towards speculative territory. Some metaphors picture the core as a planetary brain, not literally conscious, but an integrative center whose complex flows encode a kind of memory. Compared to a neural network, it is crude. It does not compute images, intentions, or plans. But it does record history in a manner of speaking. The dynamo's outputs, the spatial patterns of flux, the timing of secular variation, the signatures of torsional oscillations, are a kind of memory of past boundary conditions, sudden changes in mantle heat flux, the sinking of subducted slabs, giant impacts in deep time. These events imprint thermal and compositional heterogeneities that alter the core's flow and therefore the magnetic field. In this sense, the field is a slow, distributed chronicle of planet-scale processes. It is not a brain with agency, but it is a repository of historical signals. The other speculative axis imagines the core as an energy source, beyond mere heat, perhaps a quasi-metaphorical reservoir of concentrated power that can manifest in episodic outputs. Again, caution is essential. The core's energy is real. It is the thermal and compositional energy that drives convection, fuels volcanism, and underpins plate tectonics indirectly. But it is not an engine to be tapped, at least not by any practical means. The notion that the core could be harnessed like a battery belongs to fiction. What is useful in such a framing, however, is the perspective it affords. The magnetosphere and the ionosphere behave in ways suggestive of energy exchange and storage, with particles trapped in radiation belts, currents flowing in the magnetotail, and sudden releases during geomagnetic storms. From the vantage of life on the surface, That energy economy matters. It shapes auroras, perturbs satellites, and occasionally demonstrates that the planet's interaction with space is not merely decorative but infrastructural. The scientific community, conscientious and cautious, resists metaphors that would over-personify. Yet metaphors persist because they are rhetorically useful. They give an intelligible face to processes that otherwise remain hideously abstract. The danger lies in mistaking metaphor for mechanism. A planetary brain should be understood as a heuristic. The core's behavior integrates a history and gives back a changing field in which that history is visible. It is not sentient. Its signals are governed by fluid dynamics and magnetohydrodynamics, not by cognition. That said, the field does whisper anomalies that demand attention. Satellite systems experience increased radiation when passing through the SAA. Pipelines and long-distance cables can experience induced currents during geomagnetic storms. Cosmogenic isotopes in ice and tree rings spike during sudden influxes of energetic particles. Biological organisms are not immune. Increasing ultraviolet flux from ozone depletion, driven by energetic particle precipitation, itself modulated by geomagnetic conditions, can have ecological impacts. The paleohistory suggests that life has weathered numerous magnetic upheavals. Mass extinctions are not cleanly correlated with reversals. Still, the contemporary world is different. Human technology is magnetism, sensitive in ways that previous ecosystems were not. A weakening or rearrangement of the field has practical implications for satellites, navigation, and infrastructure at a human-relevant scale. Then, there are the truly strange signals, anomalous low-frequency pulses detected in magnetotelluric surveys, unexplained drifts in local flux that do not correspond neatly to mantle flow models, and seismic signals that couple with magnetic observatories in unexpected ways. Some of these are eventually explained. Instrumental artifacts, ionospheric storms, and localized crustal magnetizations. Others remain ambiguous, open to interpretation. The responsible scientific posture is neither credulous nor dismissive. Anomalies are invitations to refine models, expand observation networks, and seek independent corroboration. In the face of sparse data and complex models, honest uncertainty is the guiding ethic. Where does this leave human curiosity and concern? The magnetic field is a voice from the deep, composed of motions that stretch across timescales from years to millions of years. The recent acceleration of pole motion, the growth of the South Atlantic anomaly, and the cadence of geomagnetic jerks are reminders that the planet's interior is neither quiet nor static. They insist that humanity's momentary narratives, the short stories of civilization, are written across a stage whose machinery operates on far longer clocks. The field is both shield and story. It shields life from space's worst impulses, and it tells an ancient tale of iron, heat, and motion. In that tale, there is room for both steadying science and speculative wonder. The core's dynamo is a great, patient mechanism whose irregularities occasion both caution and curiosity. The anomalies recorded now do not translate into immediate doom, nor do they exhaust the imagination. They instead demand attention, investment in observation, and humility in interpretation. To listen to the field is to accept the slow pedagogy of planetary processes, to measure, to model, and to wait for the patterns to come into higher resolution. The strange signals, the drifts, the anomalies, the local weaknesses are not mysteries that must be explained away in sensational terms. They are the conversation the planet has been having in private for billions of years, now audible because humans built instruments sensitive enough to hear. The responsibility is to listen well, to translate slowly, and to live with the knowledge that Earth's heart is not a quiet, obedient thing. It is a restless partner in the long story of habitability, and its magnetic voice is both a weather report and a memoir written in flux. What if a soundless whisper began to make itself heard, not in the sky, but beneath the feet? Not in waves of light or the rush of rivers, but as an electrical murmur that no known natural process could neatly explain. The idea arrives like a small, persistent alarm on an instrument panel. A narrow-band burst recorded by magnetometers. A lower frequency pulse surfacing in magnetotelluric surveys. An odd coherence in electromagnetic noise that refuses to disappear when every known source is subtracted. It is easy enough to catalogue such anomalies as curiosities. It is far harder to do anything about them. They point, uncomfortably, to an old question pressed into hard new terms. Can humanity reach all of the planet's secrets? Or are some debts and signatures destined to remain out of touch because the physical conditions, pressure, heat, distance, exceed the practical reach of current technology? The South Atlantic anomaly sits as a convenient emblem in this story. It is a region where the magnetic shield dips and frays, where the magnetosphere's protection is locally thin and satellites feel the short, sharp sting of increased radiation. For decades, it has been catalogued, analyzed and modeled. Yet the anomaly's existence also frames a larger epistemic point. The planet's electromagnetic character is not a static background. It is an active, shifting stage upon which unexpected signals can appear, and sometimes they are not easily explained by the standard choreography of dynamo theory, crustal magnetization, or ionospheric storms. In that margin, instruments occasionally record pulses that do not fit and do not go away. The first, inevitable reaction to such data is methodological. Check the hardware, check the software, check the observers. Instruments are fallible, cables ground, sensors drift, data pipelines corrupt. Yet there are cases when anomalies survive the gauntlet of verification. When they do, they invite a catalogue of possibilities that ranges from the mundane to the unsettling. Electromagnetic signatures can be produced by tectonic strain and piezoelectric effects in certain minerals. They can be the late echo of lightning transmitted through crustal conductivity. They can be artifacts of undersea cables and industrial installations. But some recorded patterns, narrow spectral lines, reproducible pulsed sequences, or spatial coherence across widely separated stations, resist tidy attribution. They beg deeper questions and demand deeper access. Access, however, is the hard part. The planet stages its secrets in environments that are hostile in almost every dimension. Pressure at depth becomes a constant sculptor of materials. Temperature turns matter ductile and electronics fragile. Chemical aggressiveness corrodes kits intended to last only days at the surface. The human repertoire for getting down and staying down is limited. Drill rigs can burrow kilometers into the crust, but then encounter heat so severe the drill string softens and sensors overheat. Oceanic platforms lower instruments to abyssal plains and trenches, where pressure will crush a naive housing and where chemical gradients will eat at metal joints. Subglacial boreholes must reconcile sterility with extreme cold and with the ethical imperative not to pollute sealed ecosystems. The friction between intellectual appetite and physical limitation is not rhetorical. It is an engineering arithmetic that sums up to a small, stubborn number. Many of the places that could answer the electromagnetic riddles are simply out of sustained reach. Imagine, for a moment, the liturgy of an attempt. There is first the long preparatory time, a campaign of surveys from satellites that measure magnetism and gravity, airborne passes that refine resolution, seafloor magnetometer deployments that creep across a basin. Then a platform is built or a drilling rig is towed, cable is paid out by winches rated for massive stresses. Housings are manufactured to resist compressive forces measured in hundreds of megapascals. Instruments are tested at temperature and pressure extremes. Even then, when the probe reaches below a few kilometers, telemetry degrades. Signals are attenuated and smeared by the conductive medium. The very act of trying to listen at depth forces a trade-off between sampling fidelity and survivability. The narrative of such missions is full of small, painful disappointments, a log jam in a drill string that cannot be freed, an instrument that succumbs to heat slightly beyond its spec, batteries that fail before a long-duration mission can return a meaningful data set. Beyond hardware, there is a deeper, conceptual blockade. Electromagnetic signals interact with the planet's materials in ways that make their sources difficult to unmask. Conductive rocks diffuse high-frequency components. Boundaries between lithologies reflect and refract characteristic signatures. Fluids in fractures can act as waveguides, channeling energy in surprising ways. The crust and upper mantle are not a clean, homogeneous medium. They are anisotropic, fractured, chemically varied. A signal, generated at depth, is reshaped as it rises, and by the time it reaches a surface instrument, it may bear little resemblance to its origin. Interpreting these distorted messages requires not just better sensors, but far better models of how electricity and magnetism behave in complex, heterogeneous, higher pressure materials. That modeling, in turn, depends on data that can only be gathered by pushing into the very environments that are currently the least accessible. Another practical obstacle is communication. Even when a probe survives and records data at depth, getting that data out is non-trivial. Conductive materials attenuate radio. Fiber optics must be fed into the hole and kept intact under shear and creep. Acoustic telemetry through fluids is slow and noisy. Long latency becomes a real constraint. An instrument may have days to gather a signal before battery life or mechanical stability degrades, and yet the data pipeline to the surface can take hours to transmit. For autonomous systems required to act on the basis of local computations, the computational hardware must be both rugged and efficient, a combination that remains expensive and imperfect. There are, of course, alternative approaches. Remote sensing from space has matured into a powerful detective. Satellites map the magnetic field with exquisite temporal coverage. Gravity missions infer mass anomalies. Magnetotelluric soundings across continents can constrain conductivity structure by injecting and measuring natural geomagnetic variations. Neutrino tomography and muon radiography, techniques lifted from particle physics, offer tantalizing prospects for non-invasive imaging of deep mass distributions. Fiber optic cables, repurposed for distributed sensing, can turn thousands of kilometers of previously silent infrastructure into a planetary nervous system, detecting strain waves and magnetic fluctuations with surprising sensitivity. Swarms of small disposable sensors could be dispersed to create spatially dense networks. Each of these tools extends reach in important ways, but none abolish the basic constraints. Remote methods infer rather than sample. They trade the immediacy of a returned core for the scale of a planet-wide view, and their inversions are ill-posed, often yielding multiple plausible histories for the same signature. Even if instruments could be made to survive and data could be communicated reliably, interpretation remains a delicate art. When a subterranean electromagnetic pulse is logged, the field of hypotheses fans wide. Was it a transient displacement of charge associated with a sudden fluid migration? A resonance in a fractured network acting like a pipe organ under stress? An effect of core-mantle coupling modulated by a torsional oscillation? Or at the edges of imagination, a faint residue of something non-natural, a patterned, narrow-band emission that hints at technological origin? The scientific posture must be skeptical and methodical. Extraordinary claims require extraordinary evidence. Ambiguity must be tolerated and quantified. The temptation to fill gaps with narrative, to let speculation crash into certainty, is the same temptation that science exists to resist. There is also a moral dimension to the enterprise of reaching. Drilling, probing, and sampling are interventions into systems that evolved without human purpose. A borehole can create a conduit for fluids, alter pressure regimes, and change chemical equilibria. It can inadvertently introduce organisms into previously sterile niches or transform slow, stable habitats into vectors of modern contamination. The ethical calculus becomes more fraught when the signals of interest are ambiguous. If a pattern were to be interpreted, rightly or wrongly, as evidence of a past technological process, the decision to probe deeper would carry social, political, and philosophical weight beyond the usual bounds of scientific prudence. How to choose a path when the act of investigating may erase the very thing it seeks? The precautionary principle applied here is not an abstract ideal, but a practical constraint that must temper ambition. Yet, the inability to access certain depths should not be read as a failure so much as a call to reframe questions. There are different kinds of knowledge, and some demand proximity while others reward patience and synthesis. The deep earth will yield its electromagnetic secrets to instruments that are both better and deployed with a patient choreography. Incremental mapping, dense cross-validation between remote and local measurements, long-duration deployments that watch and wait, and new materials and designs built to survive in heat and pressure regimes previously deemed inaccessible. Progress will come from marriage of disciplines, geophysics with materials, science, particle physics with seismology, engineering with ethics. It will also require a social will, funding, international cooperation, standards for environmental protection, scaled to the long, slow timeline these investigations demand. There is, finally, an existential element to the hesitation. The planet's private electromagnetic utterances remind a species that has learned to shape the nearer space environment and sequence genomes of its own microbes that there are frontiers that do not yield to speed or spectacle. The current limits, pressure that crushes, temperature that softens, distance measured not just in kilometers but in orders of magnitude of energy, are invitations to humility. They ask for a different virtue than conquest, the patience to design campaigns that stretch across decades, the restraint to avoid invasive acts that preclude future knowledge, and the wisdom to accept that some signals may forever remain part of the planet's private conversation. Can they reach everything? The practical answer for now is no. There are electromagnetic murmurs and subterranean signatures that, by their context and depth, lie beyond direct, unambiguous reach. But that negative is not a dead end. It is a boundary condition that shapes how curiosity must proceed. The limits compel a shift from immediate contact to indirect mastery, better listening, better modeling, more creative combinations of observation, and a legal and ethical architecture that governs intrusion. In the end, the question is less a binary of possible or impossible than a yardstick of ambition. How much of their curiosity will humans translate into patient, collective, and cautious programs of investigation? How willing will they be to build instruments and institutions that operate on planetary timescales? And how ready are they to live with mystery as an enduring feature of their Earth? The planet speaks in many languages. Some are annexed by sight and touch, Others are written in magnetism, in chemical gradients, in pressure that would flatten the unwary. Those languages are not conspiratorial. They are consequences of the material conditions that make Earth both hospitable and inscrutable. To reach deeper is to accept that the tools must change, that the ethics must deepen, and that patience, the slow, unglamorous practice of long campaigns, careful sterilization, cross-discipline debate, and incremental learning, will be the most valuable technology of all. The electromagnetic anomalies are, in that sense, a mirror. They show not only what lies underground, but what kind of species stands at the surface, poised between hunger for knowledge and the humility to wait. What happens when a secret is not merely unknown, but dangerous to know? The question carries a particular weight when the secret sits beneath ice, under kilometers of ocean, or deeper still, in pockets of rock where heat and pressure have held back exchange for geological ages. In the slow catalogue of Earth's unread pages, there is an ethical page whose text is not carbon-dated ink, but a hazard warning. Some archives, when opened, may alter the world that opened them. The tension is elemental. Curiosity is at the core of the scientific enterprise. The urge to lift a lid, to sample a preserved pocket, to sequence a shard of ancient DNA is what has produced medicine, agriculture, and the knowledge that shapes modern civilization. But curiosity is not morally neutral when it mates systems that evolved without human observers. A sample brought into a laboratory may be a whisper of the past, or the match that sets a new kind of fire. The moral question that emerges is not simply, can they know? But, if they know, can they control what they find? There are two strands to this danger, biological and ecological. On the biological side sits the familiar spectre of pathogens, organisms whose evolutionary history tuned them to infect and reproduce within particular hosts. Some of these organisms can be remarkably durable. Spores, certain viral particles and cysts can resist cold, desiccation, and time in ways that challenge intuition. When permafrost releases ancestral microbes, or when subglacial waters are pierced, the immediate fear is that a microbe long absent from modern ecological networks might find, by accident or circumstance, a susceptible host. The narrative is not simply speculative. A real-world portent exists. Thawing permafrost has in recent decades been connected with outbreaks associated with long-buried animal carcasses, and laboratory work has recovered ancient viral and bacterial fragments from ice cores and sediments. Those facts are not evidence of impending catastrophe. They are reminders that biology can persist in unexpected forms and that retrieval is possible. But survivability is only the first hurdle. For a revived organism to become a public health threat, it must encounter congruent ecological conditions, a host that is physiologically compatible, an environment that permits transmission, and a set of selective pressures that favor its propagation. The probability space is complex and often unlikely. Many microbes that persist in cold anoxic matrices are specialized to those extremes and lack the biochemical toolkit to thrive in warm-blooded animals. Yet improbability is not impossibility, and the ethical calculus cannot rest on metaphors of rare chance when the consequences, ecological disarray, waves of illness, or destabilized food webs, could be profound. Ecological harms are broader and more insidious than pathogen emergence. Ancient organic carbon released from thawing soils or sediments can fuel microbial blooms, reconfiguring nutrient cycles and producing greenhouse gases that amplify warming. Nutrient pulses delivered to coastal seas can induce algal blooms that restructure fisheries and coastal economies. Microbial communities, once isolated for millennia, could act as ecological engineers in contemporary habitats, They may decompose previously stable carbon pools, alter redox chemistry in sediments, or outcompete native microbes in narrow niches with cascading effects on food webs. The difficulty is that ecosystems are networks of contingent interactions. Introducing a new microbial player does not produce a linear outcome. It produces a cascade whose dynamics are often chaotic, contingent on seasonality, on local species composition, and on microgeography. Predictive models can suggest scenarios, but the space of possible trajectories is large and the consequences sometimes irreversible. In ecological terms, the problem is not merely whether a particular microbial species revives, but how that revival could alter flows of energy, matter, and signaling across an interconnected biosphere. Technical capacity tempers, but does not eliminate, these risks. Modern laboratories are capable of identifying, sequencing, and characterizing microorganisms with astonishing precision. Sterile drilling protocols, cleanroom sampling, and BSL-4 containment offer methods to limit accidental release. The language of precaution, sterilize, isolate, chain of custody, quarantine has become a liturgy in fields that peer into ancient environments. For subglacial lakes and similarly sealed ecosystems, proposals for drilling insist on hot water rigs with serial filtration, ultraviolet and chemical sterilization, and multi-stage containment for any return samples. For permafrost cores, the recommendation is simple in principle and hard in practice. Keep the cold chain unbroken, minimize handling, and sequence in situ when possible. But technologies of containment face limitations. Sterilization is not perfect, filters leak, chemicals can alter the very signals scientists seek to preserve, and absolute sterility is asymptotic rather than binary. Chain of custody laws and laboratory protocols are social constructs. They function where institutions, funding, and oversight exist, and they fray at boundaries where resources and governance are sparse. The most tightly contained sample, once opened, becomes a present object in a social arena where politics, fear, and misinformation can quickly reshape response policies. The production of knowledge itself becomes a hazard when it changes public perception. An ambiguous dataset, a fragmentary sequence suggestive of an ancient virus, an isotopic anomaly interpretable as an unusual carbon input can be amplified by media and by political actors. Public panic, economic dislocation, and calls for hasty remedial measures can follow. Conversely, suppression of data in the name of preventing panic undermines public trust and can breed conspiracy. The social dynamics that surround discovery are as consequential as the physical dynamics that produce the sample. AI and robotics, often invoked as means of safer exploration, complicate rather than simplify the picture. Autonomous systems can reduce human exposure to hazardous environments and perform long-duration observations in ways that humans cannot. They can monitor water chemistry, detect anomalous emissions, and stream telemetry that flags early warning signs. But automated instruments are only as good as the models that inform them. A machine can detect an unusual gene sequence and flag it, but interpretation, assessing pathogenic potential, ecological risk, or the need for intervention requires judgment. Moreover, robotics cannot undo the consequences of opening a sealed system. They can delay and they can detect, but they cannot fully control the cascade that might follow a release. The illusion that technological mediation converts risk into neat, manageable units is seductive. Reality is messier. There are also darker rationales for concern. The dual-use problem. If an ancient metabolic pathway or an enzyme with unusual stability is recovered and synthesized, its applications could be benign. Novel biocatalysts, medical enzymes, or harmful. if used to enhance environmental persistence of engineered organisms or to fashion new vectors of disease. The capacity to read DNA and to write it again with synthetic biology is growing faster than the global norms that might govern the uses of such knowledge. The discovery of a robust cold-stable enzyme might be a boon to industry. In another context, it could be repurposed for harm. The scientific community knows this, and debates about publishing sensitive sequences or about who receives particular strains are no longer theoretical exercises. They are frontline biosecurity challenges. Ethical frameworks exist. The precautionary principle, stewardship ethics, the Outer Space Treaty's approach to planetary protection offers a useful analogue, but they often lack teeth. The Outer Space Treaty, for instance, formalized restraint in order to prevent contamination of other worlds. On Earth, restraint is less formalized despite analogous risks. International law is fragmentary. National interests, commercial pressures, and uneven capacities to manage risk mean that unilateral action can outpace collective deliberation. The result can be patchy governance. One country opens a site for study with strict containment, another declines to participate or to share data. A private firm seeks to monetize access, and an indigenous community objects to research on their ancestral lands. The ethical problem is therefore as much about epistemic justice and governance as it is about laboratory protocol. Practical policy responses cluster around a few core strategies. First is moratoria for particularly risky interventions, a global agreement to defer drilling into certain sealed environments until international standards for sterilization, oversight, and post-sampling monitoring are in place. Second is staged access, a tranche-based permissioning in which preliminary, non-invasive surveys precede any intrusive action and where each stage is governed by independent review. Third is transparency and data sharing. When ancient sequences or unusual chemical anomalies are found, pre-agreed channels for independent verification should exist, ideally under neutral international auspices. Fourth is investment in situ analytics. Instruments that analyze in place reduce the need to transport potentially hazardous material across biosecurity thresholds. Fifth is capacity building, supporting laboratories and oversight bodies across regions so that governance does not depend solely on a handful of wealthy nations. All of these measures depend on a social consensus that knowledge is not an absolute good divorced from context. They demand the willingness to prioritize long-term planetary health over near-term novelty or economic gain. In practice, achieving such consensus is difficult. Researchers are driven by funding cycles and careers. Companies are driven by returns. Politicians are driven by electoral calendars. Generating the slow, intergenerational stewardship ethic necessary to govern the opening of deep-time archives requires narratives that bridge public imagination and scientific nuance, not sensational headlines, but public-facing explanations that acknowledge uncertainty while clarifying risk. The ethics of discovery must also reckon with equity. Many ancient archives lie on or beneath territories inhabited by indigenous peoples and local communities whose knowledge systems include deep-time stewardship practices. The history of science is regrettably punctuated by extractive practices that ignored consent and dispossessed communities of both material and intangible heritage. Good practice therefore requires consultation, meaningful consent, benefit sharing where appropriate, and respect for cultural and spiritual relationships to land, ice, and sea. The decision to access a sealed lake, a permafrost plateau, or a drowned landscape is not only a technical decision, it is a social contract. Finally, there is a philosophical horizon to the debate, whether some secrets should remain secret. The impulse to read every page of Earth's book is deeply human, but it is not axiomatic that every page must be read at once. Some knowledge, once extracted, cannot be unread. The moral imagination must therefore include restraint as a form of wisdom. Abandoning research out of fear is not the point. Rather, it is about calibrating curiosity with caution, ensuring that discovery does not become harm. The plausible scenarios are many. In one, tightly controlled sampling of the subglacial lake reveals novel microbes of immense biotechnological promise and negligible risk. The sequences are published, the enzymes responsibly developed, and new insights into Earth's resilience emerge. In another, contamination during an ill-provisioned drilling campaign introduces modern microbes into an ancient niche, confounding interpretation and erasing unique evolutionary experiments. In a third, thawed sediments release carbon and nutrients that trigger unforeseen ecological shifts in coastal systems, altering fisheries and releasing greenhouse gases in a pulse. Each scenario is within the realm of possibility. Each calls for different mixes of governance, science, and public engagement. What, then, can be controlled? The answer is both practical and sobering. Many mechanical aspects can be controlled: sterilization, containment, chain of custody, high containment laboratories, and staged protocols. Early warning systems and rapid genomic characterization can provide time to react. International moratoria and shared governance can slow the pace of intrusive access until standards converge. But what cannot be fully controlled are the emergent dynamics of ecological systems, the social ripple effects of discovery, and the long-term consequences of releasing ancient molecules into a world that has changed around them. Control is partial and probabilistic. It is an exercise in risk management rather than an assurance of safety. The concluding truth is modest but consequential. The discovery of Earth's deepest secrets is no longer merely a technical challenge. It is a moral and civic test. The planet's archives are not inert curiosities. They are part of a living planet whose future depends on how knowledge is pursued. To peer into sealed chambers and frozen vaults is to accept custodianship. And with custodianship comes the duty to choose method over haste, cooperation over unilateralism, and restraint over spectacle. If knowledge is power, then prudence is its necessary temper. The species that reads the planet must ask, with steady voice and without theatricality, what are we willing to risk in order to know? And what responsibilities does knowing impose on those who survive the decades to come? 11. Humans and the instinct to explore. What is the restlessness that has pushed the species outward decade after decade, generation after generation? Put another way, where does the impulse to cross the next horizon come from, and what happens when those horizons do not simply recede, but reveal how little was understood to begin with? The narrator begins with an idea, small and insistent. Exploration is not only a set of feats, voyages, rockets, drills, but an ancestral rhythm embedded in bodies and cultures. Long before telescopes and steel hulls, the same drive moved groups to leave a familiar valley for a stranger river. A hand that learned to crack bone to pry marrow became, over countless seasons, a hand that would shape an oar, then a keel, then a composite shell for a spacecraft. The arc is not teleological, it is accumulative. Each tool is a translation of a question into action. The question remains the same: what lies beyond the frame they know? That continuity invites scenes large and intimate at once. Imagine the slow calculus of ancient decisions. Cloudy weather for days, food stores bending towards scarcity, a herd's disappearance suggesting migration, enough small pressures for a group to step onto a shoreline and push a raft into open water. The narrative does not dwell on a single hero, it follows a collective motion, an emergent strategy. Later, the same species learns to interpret the stars not as gods, but as instruments. Celestial patterns become maps, maps become charts, charts become mission plans. The transformation is not sudden, it is the accretion of curiosity into institutions, guilds of sailors, academies of astronomers, national space agencies, private labs with their own timetables and anxieties. Each expansion of reach rewrites the relationship the species has with scale. Coastal peoples learned tides and wind, mountaineers learned rockfall and altitude, navigators learned currents and compasses, astronauts learned microgravity and the choreography of orbital mechanics. There is a particular kind of exhilaration recorded in these movements, a cognitive thrill when a prediction is confirmed, when a map line becomes a coastline, when an instrument returns a photograph from a place only imagined. That thrill is also a cultural accelerator. It rewires institutions toward ever larger bets. More funding, longer campaigns, higher resolution sensors. The species prizes that acceleration because it works. It has delivered cities, vaccines, satellites, and telescopes. But a different feeling joins the exhilaration as the scale grows, a dawning humility. The narrator dwells on that inversion because it is the melancholic companion to every technological triumph. The more the species learned, the more it discovered the seams in its knowledge. Landing robotic feet on Mars was not merely evidence of capacity, it was a mirror that reflected their own unread pages. Outward exploration. To the Moon, to Mars, to probes beyond the heliosphere, made visible how thin was the species' knowledge of its own home. It looked outward for the grand unknown and found, to its surprise, that the nearest unknowns were still underfoot and undersea. This is where a large montage of human endeavour grows into a reflective scene. There is the sound of a drilling rig's rotation, a ship's winch releasing line, the hush of a satellite's comms link establishing contact, scientists in labs hunched over thin ice cores and basalt chips. Each action is described in its technical detail. Torque measured, cores logged, sonars swept. Those details serve as proof of intent and as counterpoint to the quiet fact repeated throughout the earlier parts of the narrative. An enormous fraction of the planet remains only faintly sketched. The species has machine-mapped neighboring worlds with a fidelity greater than that of its own abyssal plains. Telescopes have imaged exoplanets, and yet whole trenches and frozen lakes were, until recently, still the province of speculation. Emotion threads through these technical motions. There is persistent curiosity. The same trait that once led ancestors to follow, migrating herds, now animates multinational expeditions that drop camera-lit submersibles into endless black. There is anxiety, an awareness that moving into a new domain may change the domains already known. There is wonder at the inventiveness that allows humans to measure hydrogen in a subglacial lake or to coax isotopes from a rock. And, increasingly, there is an ethical unease. If knowledge can be taken, should it be taken uncritically? If the planet's archives are fragile, is possession of a sample equivalent to stewardship or to looting? The long scene of exploration stretches into institutional contours. Universities that once rewarded speculative scholarship now reward data sets. Funding agencies prefer deliverables and near-term impact. Private enterprises see the seafloor and the polar shelves as domains of resource prospecting. These pressures shape what gets studied and how. Practical constraints, budget, politics, logistics, bias. Curiosity toward projects with clear returns. The narrator does not condemn this bias. Instead, it notes the structural consequences. To chart a trench at high resolution requires not only ingenuity in engineering, but a value system willing to prioritize patient, costly work over flashy results. That priority is not automatic. There is a philosophical aside here. Exploration itself changes the explorer. The species that builds instruments to measure deep pressure and cold acquires new metaphors. Time is no longer only the pulse of a day or the ledger of a human life. It expands into glacial time, into the slow churn of subduction, into the quiet chemistry of a core that gyrates on scales measured in millions of years. That shift rewires narratives of identity. A civilization once centered on immediate human timescales begins, faintly, to practice patience. The narrator lingers on that possibility because it matters. The humility learned in listening to the world's slow languages, ice cores, sediment layers, magnetic anomalies, becomes an ethic. It tempers the species' appetite for conquest with a sense of custodianship. Yet the instinct to explore does not simply bow out. It evolves. The same curiosity that pushed wooden ships into storms now builds long-duration observing platforms, networks of autonomous vehicles, sterile drilling rigs, and satellite constellations. Institutions invent new rituals to match long timeframes, data preservation schemes that plan beyond political cycles, international committees to arbitrate access to fragile archives, and layered consent processes intended to include local and indigenous voices in decisions about places that hold ancestral stories. There is an emerging vocabulary that couples discovery to responsibility. The paradox remains central. The more humans press outward, into space, into machine intelligence, into synthetic biology, the more they meet limits grounded in deep time and deep process. That encounter is not a failure, but a reorientation. Discovery is less often a conquest and more often a lesson in listening. The species must learn new instruments of patience, technologies designed for endurance, funding models that reward stewardship, and a public ethic that privileges cumulative knowledge over instantaneous spectacle. In closing this part of the narrative, the narrator offers a compact image. The species as an animal that has learned to light fires and then, centuries later, to build probes. That continuity conceals a deeper moral. Mastery of technique is not identical to mastery of wisdom. Instruments can pry open vaults. They cannot, by themselves, teach restraint. The ongoing drama of exploration, then, is not only about going farther, but about deciding how to go and why. 12. Conclusion. The silence. If the narrative of exploration bends toward responsibility, then the end must return to a quieter register, a question that is as ethical as it is epistemic. When most of a world's own pages remain unread, what kind of readers will the species be? The narrator opens with a provocative image, not a landscape, but a silence. It is the silence of unmapped trenches, of ice that has not surrendered all its bubbles, of cores that have not yet been pulled. Silence here is active. It is not absence alone. It is the planet's manner of speech, a microphone turned down by pressure, by cold, by time. Under that silence there is information, but it is encoded at tempos and in grammars foreign to human impatience. The species can choose to break the silence quickly and clumsily, or to learn the disciplines of patient listening. The conclusion unfolds through three interwoven considerations: knowledge and humility, curiosity and caution, and stewardship and responsibility. Knowledge and humility. The narrator revisits the surprising lesson repeated across trenches, ice sheets, and boreholes. Earth preserves and erases according to its own economies. Pressure buries, heat transforms, flows recycle. The planet's archives are partial, and biased towards certain preservation pathways. The implication is stark. Claims about deep pasts, whether biological or cultural, must be framed probabilistically. Finding an anomalous isotope ratio or an odd sediment layer is not proof of past civilizations or impossible life. It is a hint that must be interrogated with a patient, multidisciplinary lens. Humility is a methodological necessity. A scientist who recognizes the planet's erasure mechanisms, frames hypotheses with conditional language, and constructs experiments that minimize contamination and maximize reproducibility. Curiosity and caution. Curiosity remains the species' oldest virtue, yet the conclusion insists that curiosity unmoored from caution becomes a hazard. The narrative lists practical tools of caution: staged access to sealed systems, pre-registered protocols for sterilization, in situ analysis where possible, transparency of data and methods, and independent verification before sensational claims are made public. These are not bureaucratic barriers, they are epistemic safeguards. The species has, in other domains, learned similar rules. Clinical trials, environmental assessments, arms, control treaties. Applying parallel disciplines to the planet's deep archives honors both the desire to know and the duty to preserve. Stewardship and responsibility. The narrator widens perspective beyond instruments and labs to include communities and time. Many of the places of interest, polar ice, submerged continental shelves, glacial forefields, intersect with indigenous territories and with societies whose lifeways will be directly affected by discoveries and interventions. Ethical exploration requires partnership, meaningful consent, and shared decision-making. It also requires intergenerational thinking. The cores and samples taken today will become part of a cultural and scientific legacy that future generations inherit. The species must therefore weigh the immediate benefits of knowledge against the rights of those who will come after. The tone here is not prescriptive moralizing, but a set of pragmatic commitments. The narrator suggests concrete principles rather than commandments. Prioritize non-invasive surveys before intrusive sampling, require independent environmental review for high-risk operations, build global agreements that treat certain sealed systems as commons to be protected, invest in situ analysis and long-duration monitoring over one-off extractions, and cultivate a culture of scholarship that prizes replication, open data, and humility in interpretation. There is a final, elegiac movement in the conclusion that seeks neither to dampen ambition nor to romanticize ignorance. Rather, it asks for an adult stance toward curiosity. The species must accept that the planet's deepest pages will not be readable on a human timetable. They will require listening technologies, patient funding, and cross-cultural stewardship. Some answers will arrive in months, others will come centuries later. That tempo is not failure. It is a constraint that, if embraced, reshapes curiosity into a sustaining, intergenerational practice. The narrator closes with an image that returns to the initiating question about silence. The planet's most intimate archives, its dark abysses, its frozen vaults, its inner convective heart, are not mysteries to be beat back by force, but conversations to be earned. Silence, then, is not merely a lack, it is a condition for reverence. It offers the possibility that when the species finally reads more of Earth's story, it will do so with a humility that honors the planet's timescales, an ethics that protects its fragile records, and a curiosity tempered by responsibility. In that final hush, the narrator leaves one last quiet imperative: to listen longer, to act more cautiously, and to remember that the greatest discoveries are not those that render the planet legible in an instant, but those that add one careful page to a story meant to be read slowly. across generations, across disciplines, and with the restraint of those who have learned what it costs to break the silence. What if the most telling statement about a world is not a roar of discovery, but a long, patient silence? The idea arrives not as a picturesque horizon, but as a question. What does it mean, ethically and epistemically, to stand in the long hush of places the species has not read? The abyssal plains, the sealed lakes beneath ice, the dark pores of continental crust, and to recognize that silence itself contains information. This is the thought that closes the sequence, and it demands a kind of attention the species has rarely cultivated. Not the instantaneous applause of a single revelation, but a slow apprenticeship in listening, interpreting, and restraining impulse. Silence, in this sense, is active. It is not an absence that begs to be filled by any instrument at hand. It is a condition shaped by processes and constraints. Pressure varies, heat converts, fluids diffuse, and time reworks texture and chemistry into patterns that are faint and ambiguous to instruments tuned for immediacy. The unmet majority of the ocean, the kilometers of ice that have never been bored, the crustal volumes untouched by a clean drill. Each keeps counsel on its own terms. That counsel is encoded in gradients of chemistry and magnetism, in isotopic ratios, in battered and rarefied biomolecules, and in the slow choreography of flows and sediments. To treat silence as a mere void is to misunderstand the planet's method. To translate it requires tools, protocols, and a moral imagination matched to deep time. There are three truths that emerge from taking that silence seriously, each of them practical and ethical rather than mystical. First, absence is evidence. The lack of an obvious archaeological signature on an abyssal plain is not proof that no complex history unfolded there. It is instead testimony to the planet's economy of erasure. Sedimentation rates, turbidity currents, chemical corrosion, and tectonic recycling conspire to transform structures and molecules into distributions and anomalies. The right question, then, is not simply what lies there, but what forms of evidence survive these processes, and how can they be distinguished from geological noise? That rephrasing shifts attention from sensational imagery to lower signal, higher certainty science. Isotopes, trace, metal, anomalies, statistical outliers in sediment composition, and patterns of genetic fragment attrition that bear the fingerprint of age rather than of modern contamination. Second, curiosity must be married to precaution. The same tools that make discovery possible also make disturbance inevitable. Drills pierce seals. Boreholes create conduits for fluid exchange. Sample retrieval risks, introducing organisms into new ecological contexts. The precautionary principle is not an abstract moral posture in these domains. It is a practical safeguard. It must be operationalized into staged access, non-invasive surveys followed by minimally invasive probes, mandatory sterilization standards tailored to environment and depth, independent environmental review panels, and binding transparency requirements for methods and data. These conditions are not meant to throttle inquiry, but to preserve the integrity of the questions being asked. A rushed extraction that contaminates a subglacial lake destroys the very historical record that justified the campaign. There is no discovery of value equal to the loss of an irreplaceable, closed ecosystem. Third, responsibility is intergenerational and distributive. The archives that climate change now exposes, thawing permafrost, newly exposed coastal shelves, ice cores being released earlier than planned, affect not only current communities but legacies that run centuries and millennia forward. Decisions about when and how to sample are decisions about what future readers will be able to learn. They implicate transnational governance structures, indigenous and local rights, and the question of who gets to interpret Earth's deep past. Stewardship cannot be outsourced to a small set of institutions or states. It demands inclusive governance, capacity building for laboratories in diverse regions, and processes that ensure benefit sharing and meaningful consultation where ancestral lands and waters intersect with sites of scientific interest. Practically, respecting silence requires concrete architectures of practice. The first is a universal hierarchy of interrogation. Remote sensing and non-invasive surveys should be the default first step. Satellite magnetometry, airborne gravity and LiDAR, seafloor multibeam surveys, autonomous vehicle reconnaissance, and magnetotelluric soundings create a map of plausibility before any intrusive act is permitted, where probability density for meaningful archives concentrates. Staged microprobing can begin. In situ sensors that perform chemical and genomic assays without returning bulk material to the surface. Only after repeated, independently verified in situ signals should an extraction be considered. And then, only under strict containment protocols, chain of custody rules, and international oversight. The second architecture is technical. Investment in tools designed to minimize contamination and maximize on-site analysis. Hot water drills with serial sterilization, closed-loop sampling pods, deep-sea observatories that can perform molecular sequencing in situ, and autonomous long-duration platforms are not luxuries, but necessities. They shift the epistemic burden from returning samples to analyzing them in context. Distributed fiber optic sensing, repurposed along subsea cables, networks of magnetometers with open data streams, and satellite constellations focused on temporal coherence, rather than singular snapshots, will expand the listening capacity of the species without proportionally increasing the footprint of intrusion. The third architecture is governance. The creation of multilateral accords that treat certain environments as commons with custodial rules. Such accords should enshrine principles of consent, making research contingent on consultation with affected communities, including indigenous peoples whose oral histories and stewardship practices often intersect with the science in complementary ways. They must also define protocols for data sharing and independent verification, preventing premature sensationalism and ensuring that claims of extraordinary significance are subject to reproducible evidence. International review boards for high-risk interventions are necessary, and the funding mechanisms that support long-term observing campaigns must guard against capture by short-term political cycles or commercial incentives that prioritize resource extraction over knowledge integrity. All of this must be sustained by a cultural shift within the institutions that drive exploration. Universities, funding agencies, private enterprises, and national scientific bodies must value patience as an epistemic virtue. Reward structures should not privilege immediate impact over careful, replicable discovery. Career incentives, grant cycles, tenure committees, and publication norms must broaden to reward stewardship. Replication, data curation, robust negative results, and long-duration monitoring. That shift is as much about narratives as it is about dollars. The public story of exploration. The news cycles that reward dramatic imagery should be balanced by consistent storytelling about the long arcs of inquiry and the stewardship commitments that make reliable knowledge possible. Emotionally, the silence of the planet engages a complex palette. There is, first, awe. An almost spiritual recognition that the Earth is a multi-layered archive whose depth dwarfs human lives. That awe has a clarifying effect. It tunes the species toward humility. There is also anxiety. a recognition that rapid environmental change is unsealing documents before proper protocols are in place. That anxiety can either precipitate panic-driven intervention or catalyze the political will to construct the very safeguards just described. Finally, there is a mournful tenderness for the fragility of archives and for the awareness that some discoveries, once made, cannot be undone. These feelings are legitimate data. They shape risk perception, policy appetite, and the cultural narratives that will sustain intergenerational stewardship. The silence is not simply a challenge to methodology, it is an invitation to a different kind of science, one that is inherently interdisciplinary, transnational, and reflexive. Reading Deep Time requires geophysicists who appreciate biochemistry, biologists who understand sedimentology, ethicists who can translate risk into protocols, and communities who provide legitimacy and local knowledge. It is an intellectual culture that prizes careful translation across languages of evidence, isotopes to narratives, gene fragments to evolutionary histories, mineral anomalies to tectonic episodes. The productive virtues here are patience, replication, and humility. There are, inevitably, pragmatic tensions, commercial pressures to mine polymetallic nodules or to exploit Arctic passages create incentives to accelerate exploration. National security considerations. The strategic value of subsurface resources or the imperative to understand climate-driven sea level change will push some states toward unilateral action. That is precisely why institutional safeguards are necessary. Scientific norms alone cannot withstand geopolitical incentives. International law, cooperative funding mechanisms, and binding environmental impact assessment obligations will be essential to ensure that curiosity does not become a vector for irreversible harm. At the same time, silence itself can be an ally to good science. It forces the acceptance of negative results and probabilistic claims. A layer of sediment that lacks a clear anthropogenic signature is a finding. The absence of the smoking gun is a constraint on models of the past. The dialogue between absence and presence, between signal and null, is where scientific judgment is sharpened. Good practice recognizes that some questions will be answered not by a single artifact, but by accumulating independent threads of evidence accrued over decades. In practical terms, the species should pursue a set of concrete priorities in the immediate decades ahead. First, build global, long-term observatories, arrays of autonomous sensors across the abyssal plains, sustained satellite missions for geomagnetic monitoring, and networks of ice sheet stations that combine meteorology, geophysics, and molecular sampling. Second, establish robust international protocols for access to sealed environments, including moratoria, where risks are demonstrably high, and standards for sterile access, where intervention proceeds. Third, expand in situ analysis capabilities so that the default is to measure before moving materials. Fourth, institutionalize community consultation and consent into research planning, ensuring that local and indigenous peoples are partners rather than passive subjects. Fifth, fund capacity building in under-resourced regions so the governance of discovery is genuinely global. None of this promises rapid closure of the planet's unread pages. Many answers will arrive only with patience. Isotopic reinterpretation that requires decades of core accumulation, genetic signals that need cumulative datasets to be disentangled from contamination, geodynamic models that sharpen only as seismic networks densify. The virtue is not in haste, it is in the discipline to build the informational commons that future interpreters will need. The final insistence of this closing chapter is modest. The species can do better than pry and pollute. It can cultivate custodianship, listening longer is not a retreat from curiosity, it is a maturation of it. Curiosity informed by restraint becomes a practice of care, care for the records of deep time, care for present ecosystems, and care for the rights of future readers. The planet's silence is not a lacuna to be filled by spectacle. It is a test of how a species converts curiosity into wisdom. In that long hush, an imperative remains to learn the grammar of the Earth's slow languages and to answer them with instruments and institutions built for endurance. The greatest discoveries will be those that arrive without wrecking the conditions that made the discovery possible. The planet's deepest archives are not trophies. They are parts of a living system whose integrity matters to the future. To break the silence respectfully requires patience, shared stewardship, and a recognition that some secrets, once pried open, cannot be resealed. So let the final note be an invitation rather than a command. The species must choose to listen, to wait, and to act with measured curiosity. Each careful page read, each verified isotope ratio interpreted, each sterile sample catalogued will expand knowledge not instantaneously but cumulatively, a library assembled across generations. In the hum of instruments and the patience of scientists, and in the deliberations of global institutions and communities, the silence will, slowly and responsibly, begin to speak. When it does, it will do so to listeners who earn the right to hear,